The nearest star to our sun sits 40 trillion kilometers away. If you started walking there right now, your descendants would arrive in 900 million years. Not you, not your children, not even your species would likely survive the journey. Voyager 2, the fastest object humanity has ever built, would take 80,000 years to reach it. That's 4 times longer than recorded human history, 4 times longer than pyramids, empires, languages, and everything we call civilization. But here's what keeps me awake at night. That's not even the strangest part of this story. The strangest part is what we discovered on the way there, on a frozen giant where diamonds fall like rain, where seasons last longer than human lifetimes, where silence itself has become a mystery that scientists still can't explain 40 years after seeing it up close. And then beyond that frozen world, across an ocean of absolute nothing, waits a red dwarf star with a planet that might, just might, be screaming with life. Today we're going to trace 2 journeys, one to the edge of everything we know, another to the edge of everything we can imagine. And by the end, you'll understand why the universe has built walls we may never climb. Let me show you why distance in space isn't just a number, it's a prison. Uranus drifts 3 billion kilometers from Earth. When you look at it through a telescope, you're seeing its past. Light takes nearly 3 hours to travel from that world to your eyes. 3 hours. By the time you see Uranus blink, that blink already happened while you were eating lunch. Now imagine trying to control a spacecraft there. You send a command, turn left. 3 hours pass before the signal arrives. The spacecraft executes the turn. 3 hours pass before you know if it worked. 6 hours total. In that time, your spacecraft could have drifted into a moon's gravity well, or passed through a debris field, or simply malfunctioned while you sat on Earth waiting for confirmation that never comes. This is what distance does in space. It doesn't just separate you from a place, it separates you from time itself. 20 times farther from the sun than Earth, Uranus hangs in perpetual twilight. The sunlight there feels nothing like the warmth you know. It's not golden, it's ghostly, dim to the glow of a winter sunset that never ends. Stand on Uranus, and the sun becomes just another bright star, casting light so faint that shadows blur and dissolve before they can form. The warmth that feeds our world barely touches this distant giant. Every photon that reaches Uranus has traveled for hours, exhausted by distance. By the time it arrives, it carries almost no heat, just a whisper of energy. Enough to illuminate but never to warm. Temperatures plunge to minus 224 degrees Celsius, the coldest atmosphere ever measured in our solar system. Colder than Neptune, even though Neptune sits farther from the sun. Think about that paradox. The planet closer to our star is somehow more frozen than the one deeper in the outer darkness. This shouldn't be possible. Most planets radiate heat, leftover energy from their violent birth billions of years ago. Jupiter glows in infrared. Saturn broadcasts warmth into space. Neptune pumps out twice as much energy as it receives from the sun, still burning through the heat of its formation. But Uranus radiates almost nothing. Its internal heat is gone, snuffed out, as if millions of years ago something reached inside and turned off its fire. Scientists have theories. A catastrophic impact, they say. Something massive, perhaps the size of Earth, slammed into Uranus in the ancient past. The collision was so violent, it tilted the planet on its side and vented its core heat into space. The energy that should have sustained it for billions of years was released in a single, apocalyptic moment. Or maybe the planet's layered atmosphere traps cold in ways we don't understand yet, prevents convection, locks away what little warmth remains in unreachable depths. Whatever happened, the result is a world that feels extinguished, not just cold, but dead, a planetary corpse frozen in eternal meditation. At minus 224 degrees, molecular movement nearly stops. Atoms forget how to vibrate. Every whisper of warmth drains away into the void. Sound waves die before they can propagate through the dense, frigid gases. Storms that would roar on Earth become silent ballets here, moving in glacial slow motion through clouds that never see daylight. Hydrogen and helium, gases on Earth, become sluggish fluids on Uranus. Water exists in forms we have no names for. Not ice, not liquid, but something in between. A pressurized slush, buried under kilometers of atmosphere, crushed by weight into exotic states of matter. Methane freezes into crystals that drift like snow, glittering faintly in the dim blue light. Each molecule moves with reluctance, obeying the rhythm of a world that has forgotten warmth. From orbit, Uranus glows softly cyan, a calm, distant orb reflecting the sun's pale touch. Serene, peaceful, deceptively simple. But that serenity hides something. Beneath those featureless clouds lies crushing pressure, perpetual night, and violence on a scale that defies comprehension. The planet's tilt adds another layer to this cosmic strangeness. 98 degrees. Unlike Earth, which spins upright like a top, Uranus rolls around the sun like a barrel tumbling through space. Astronomers call it the strangest tilt in the solar system, and they're not exaggerating. Each pole takes turns basking in sunlight for 42 years, then plunging into 42 years of total darkness. Imagine being born in spring, you graduate school in summer, start a family in autumn, grow old in winter, and only then does spring return. This isn't just a curiosity, it's a nightmare for anything that might try to survive there. One hemisphere bakes under constant radiation for decades. The other freezes in endless shadow. The temperature gradient drives winds at 900 kilometers per hour, hurricanes that circle the planet without ever stopping. Near the equator, twilight is permanent. The sun never rises or sets properly. It just traces lazy circles near the horizon, creating an endless dusk that belongs neither to day nor to night. The entire planet exists suspended between motion and stillness, between light and dark. Scientists believe this bizarre tilt came from violence. Billions of years ago, a protoplanet perhaps the size of Earth collided with Uranus. The impact didn't just knock the planet sideways, it fundamentally changed its internal structure. The blow scattered heat, scrambled its core, and sealed away energy that should have kept the planet warm. The Uranus we see today is a survivor of catastrophe so ancient its scars have frozen into symmetry. The chaos has become calm, the violence has become grace. What was once destruction is now simply the way things are. This sideways orientation creates light patterns found nowhere else in our solar system. When one pole faces the sun, it receives unbroken daylight for decades. The opposite hemisphere remains locked in night, its frozen clouds reflecting only starlight and the faint glow of distant moons. If you could stand near Uranus's north pole during summer, you'd watch the sun trace a path overhead for years without ever setting, a ring of fire circling the horizon, low and constant, painting the methane haze in shades of amber and rust. No sunrise, no sunset, just eternal noon, fading gradually as the decades pass, until one day the sun finally dips below the horizon, and then darkness reigns for another 42 years. The transition between these extremes drives massive atmospheric changes. When sunlight finally reaches a pole after decades of darkness, gases expand violently, circulation patterns shift, winds accelerate, storms brew in the depths, their methane clouds rising and falling like blue oceans beneath a foreign sky. Yet through telescopes, Uranus appears almost featureless, a smooth sphere of cyan, unmarked by the dramatic bands of Jupiter or the violent storms of Neptune. All its fury hides beneath layers of calm, like secrets whispered under breath. Even its rings and moons orbit in this tilted plane, circling the planet like a halo lying flat on a table. From Earth, we see them edge on or face on, depending on Uranus's position in its orbit. The entire system seems to defy the orderly alignment of the solar system, a celestial act of quiet rebellion. Perhaps that's what makes Uranus beautiful in its own way. Its tilt reminds us that perfection often begins with chaos, that even catastrophe can become elegance given enough time. What was once a violent collision is now a gentle roll through the dark, a planet eternally leaning toward mystery. If Earth is the dancer and Jupiter the king, then Uranus is the dreamer, turning slowly on its side, eyes half closed, following a rhythm that belongs only to itself. But beneath those calm azure layers lies something that transforms our understanding of planetary physics entirely. Something that sounds like myth, but is confirmed by laboratory experiments and theoretical models, validated by some of the brightest minds in planetary science. Deep within Uranus, where pressure climbs to millions of times Earth's atmosphere, where temperatures soar to thousands of degrees, not from sunlight but from the crushing weight of the planet itself, carbon atoms undergo a transformation. Methane gas, abundant in the planet's atmosphere, gets torn apart by heat and pressure. Hydrogen strips away, pure carbon remains, and under the immense weight of thousands of kilometers of ice and gas, those carbon atoms crystallize into diamonds, not small diamonds, not the gems you see in jewelry stores. We're talking about crystals the size of mountains, falling through layers of exotic matter in endless cascades that have continued for billions of years. This is diamond rain, a phenomenon so extreme, so alien, that when scientists first proposed it, many dismissed the idea as theoretical fantasy. Surely nature couldn't be that spectacular, that wasteful, that beautiful in places where no one would ever witness it. But in 2017, researchers recreated the conditions of Uranus in a laboratory. They compressed methane using powerful lasers, mimicking the immense pressures found deep within ice giants. The result was stunning and irrefutable. Carbon didn't just transform, it crystallized instantly, into pure diamond. For the first time, diamond rain was more than theory. It was demonstrated reality, proven in a chamber that glowed like a tiny star for a fraction of a second before the pressure released. Now imagine this process scaled up to planetary dimensions. Millions of tons of diamonds forming every second. Microscopic crystals at first, drifting like snowflakes through dense methane air. As they descend, pressure grows and crystals merge, hardening into gems larger than anything found on Earth. Some might grow as large as pebbles, others become boulders. Still others merge into structures the size of buildings, tumbling downward through layers of supercritical fluid, through regions where matter behaves unlike anything we experience on Earth's surface. They fall thousands of kilometers. Lightning flashes through methane clouds above them, illuminating these cascading jewels for fractions of seconds before darkness returns. Each bolt ignites a trillion tiny reflections, turning the depths of Uranus into a light show of brilliance and silence that no eye will ever witness. The diamonds don't settle at the core. They fall until they reach depths where temperatures become so extreme that even diamond melts. Solid brilliance turns back into liquid carbon, mixing into a sea of shimmering elements that might extend for thousands of kilometers. And then, through convection or other processes we barely understand, some of that carbon rises again, cools, crystallizes, falls once more, an endless cycle, a heartbeat within the frozen giant's soul. This process might explain one of Uranus's greatest mysteries, its missing heat. Unlike Jupiter and Neptune, which radiate excess energy, Uranus is eerily cool. Scientists think those sinking diamonds carry thermal energy deep into the interior, transporting heat to layers where it can no longer escape into space. The planet cools from the inside out. Its beauty literally drains its warmth away, dimming itself into quiet perfection. If you could somehow stand above those clouds, protected from the crushing pressure and lethal cold, perhaps you'd hear something. Not thunder, not wind, but a crystalline whisper, the sound of diamonds brushing against each other as they descend into blackness, like wind chimes made of pure carbon playing melodies that predate human existence. Here, beauty and physics become inseparable. The universe, indifferent yet poetic, has found a way to turn cold and pressure into art. In the hidden heart of Uranus, storms of solid light fall endlessly, proof that even in the darkest, coldest places, the cosmos still finds ways to shine. On Earth, a single carat of diamond costs thousands of dollars. Entire industries revolve around mining, cutting, and selling these precious stones. Wars have been fought over them, empires built on their value. On Uranus, trillions of tons rain down every second, wealth capable of buying 1,000 worlds, falling uselessly through an atmosphere where no one will ever claim it, priceless and meaningless simultaneously. The perfect metaphor for space itself, beauty that no one will appreciate, treasures that remain forever out of reach, wonders that exist only to exist. And yet, for all this magnificence hidden beneath clouds of methane and veils of distance, Uranus remains one of the most ignored worlds in our solar system, overlooked, forgotten, silent in ways that disturb scientists who study it. In the symphony of planets, every world has its sound. Jupiter roars with thunderous radio waves that crackle across millions of kilometers. Saturn sings in plasma tones, haunting frequencies generated by interactions between its magnetic field and the solar wind. Even Mars whispers through seismic tremors detected by landers on its rust-red surface. But Uranus? Uranus is the silence between the notes. When Voyager 2 approached in January 1986, scientists expected to detect something. A magnetic hum, a plasma pulse, any kind of electromagnetic rhythm that would reveal the planet's inner workings. Instead, they encountered near-total quiet. The magnetosphere was faint, oddly tilted, and offset from the planet's core by almost 60 degrees. That tilt alone defies everything we understand about planetary magnetic fields. On Earth, our magnetic field aligns roughly with our rotation axis. The magnetic North Pole sits near the geographic North Pole. Same with Jupiter, Saturn, Neptune. Their magnetic fields follow predictable patterns generated by churning metallic hydrogen in their cores. Uranus broke all those rules. Its magnetic field axis tilts wildly away from its rotation axis, as if something reached inside billions of years ago and scrambled the planet's internal dynamo. The field doesn't even originate at the center. Magnetometer readings showed the source displaced toward the southern hemisphere, perhaps a third of the planet's radius away from the core. Scientists struggled to explain this. Some proposed that Uranus's magnetic field was caught mid-reversal, like Earth's field occasionally flips poles over geological timescales. Others suggested the planet's extreme axial tilt disrupted normal convection patterns in its interior, creating a lopsided dynamo. But the weirdest part wasn't the tilt. The weirdest part was the emptiness. Voyager 2 detected almost no plasma in Uranus's magnetosphere. Plasma, the fourth state of matter composed of charged particles, should have been abundant. 5 large moons orbit within the magnetosphere. Icy worlds bombarded by radiation should release water molecules, which then get stripped into hydrogen and oxygen ions that populate the magnetic bubble. Yet Voyager found a vacuum, a magnetosphere mysteriously depleted of the very material that should have filled it. Scientists coined the term for what they observed. Uranus has a vacuum magnetosphere. How could 5 moons be completely inactive? Were they geologically dead, frozen solid without any outgassing or surface activity? The readings suggested something impossible. Moons that should have been spewing ions into space were somehow silent, contributing nothing to the magnetosphere. And then there were the radiation belts. Despite the lack of plasma, Voyager detected intense electron radiation belts, second only to Jupiter's. Electrons whipping around the planet at relativistic speeds, trapped in magnetic field lines, creating radiation zones that would fry any spacecraft trying to orbit there for extended periods. Where did those electrons come from if there was no plasma source? How did they get energized to such extreme levels? The physics didn't add up. For 38 years, these mysteries remained unsolved. Uranus stood as the strangest magnetic environment in the solar system. Textbooks described it as an anomaly, a cautionary tale about assuming planetary physics followed universal rules. Until November 2024, a team of researchers led by Jamie Jasinski at NASA's Jet Propulsion Laboratory decided to look at the Voyager 2 data differently. Instead of focusing on the 6 hours of close approach, they examined 8 months of solar wind measurements leading up to and following the encounter. What they found changed everything we thought we knew about Uranus. Days before Voyager 2 arrived, a massive burst of solar wind erupted from the sun, a coronal mass ejection, a blast of charged particles and magnetic fields that rippled through the solar system at millions of kilometers per hour. When this wave reached Uranus, nearly 3 billion kilometers from the sun, it compressed the planet's magnetosphere like a giant hand squeezing a balloon. The researchers calculated that solar wind dynamic pressure increased dramatically in the days before the flyby. This compression reduced the magnetosphere's volume by a factor of 5. The dayside magnetic bubble, normally extending perhaps 28 Uranus radii into space, got squashed down to just 17 radii. And that compression explained everything. When you squeeze a magnetosphere, you push plasma out. Like squeezing a sponge, charged particles get expelled from the magnetic field lines. The moons were releasing ions. They were geologically active. But the solar wind blast had emptied the magnetosphere just before Voyager arrived. Simultaneously, that compression drove electrons deeper into the radiation belts, accelerating them to extreme energies. The intense radiation Voyager detected wasn't a permanent feature of Uranus. It was a temporary consequence of the solar storm. The team calculated that such extreme solar wind conditions occur at Uranus less than 4% of the time. 4%. Voyager 2 happened to arrive during one of the rarest magnetospheric states possible. If the spacecraft had arrived just 1 week earlier, when solar wind pressure was 20 times lower, it would have encountered a completely different planet. A magnetosphere extended and relaxed, plasma filling the space between the moons, radiation belts at normal levels, a world that resembled Jupiter or Saturn more than the bizarre vacuum environment scientists have been studying for 4 decades. Think about that. Our entire understanding of Uranus's magnetosphere, taught in universities, published in thousands of papers, used as the canonical example of an extreme magnetic environment, was based on measurements taken during conditions that exist only 4% of the time. We've been studying an anomaly and calling it normal. We saw Uranus on its worst day and assume that's how it always looks. This revelation has profound implications. It means the 5 large moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are likely active. They're releasing material into space, perhaps from subsurface oceans warmed by tidal heating. Uranus might have a system similar to Saturn's, with moons contributing to a dynamic, plasma-filled magnetosphere. It also means that future missions to Uranus will encounter a very different world than Voyager described. The next spacecraft to visit won't find a vacuum. It will find a rich electromagnetic environment, possibly with auroras, plasma interactions, and moon magnetosphere coupling that we've never observed. But here's the haunting part. We might never know what Uranus really looks like under normal conditions until another spacecraft goes there. And when will that be? NASA and ESA have discussed missions, but nothing is scheduled before the 2040s at the earliest. That's 20 years away, 2 more decades before we can revisit a world we visited only once, for 6 hours during the worst possible circumstances. And speaking of that visit, let's talk about the journey that made it possible. The loneliest mission in the history of space exploration. August 20th, 1977, Cape Canaveral, Florida. A Titan IIIe rocket stands on the launch pad carrying a probe the size of a small car. Voyager 2, destined for the outer solar system, Its mission, fly past Jupiter, Saturn, Uranus, and Neptune in a grand tour made possible by a rare alignment of the outer planets that occurs once every 176 years. The engineers gave it a 5% chance of success. 5%. The spacecraft had to survive radiation at Jupiter, thread through Saturn's ring plane, then coast for 5 more years to reach Uranus without any major failures. Charles Colhayes, one of the mission designers, later said he never truly believed both Voyagers would survive to Neptune. The distances were too vast, the time frames too long, the potential failure points too numerous. But Voyager 2 was built by people who understood the stakes. Every component was redundant. Every system had a backup. The spacecraft carried 3 computers, each one less powerful than a modern calculator, programmed to make autonomous decisions if communication with Earth failed. And Earth was getting very far away. 9 years. That's how long it took to reach Uranus. 9 years of coasting through the void at 55,000 kilometers per hour, faster than any bullet ever fired. Yet even at that speed, crossing 3 billion kilometers required almost a decade of patience. Imagine being on the engineering team. You launch this probe when you're 28 years old. You monitor its health as it passes Jupiter, watch its discoveries at Saturn, and then you wait for 5 more years. 5 years of checking telemetry every day, making tiny course corrections, hoping nothing breaks in the cold darkness between Saturn and Uranus. By the time Voyager 2 reached Uranus, those engineers were 37. They had aged 9 years waiting for 6 hours of science. The spacecraft approached from below the orbital plane, coming up toward Uranus's south pole. As it closed in, the planet grew from a pale dot to a cyan disk. Cameras captured images every few hours, watching for atmospheric features, looking for storms or bands like Jupiter's. They found almost nothing. Uranus appeared featureless, a smooth sphere of methane haze without dramatic cloud patterns. Only through computer processing did faint bands emerge, subtle variations in brightness that hinted at winds and weather hidden beneath the calm exterior. Then came the discoveries. 11 new moons emerged from the darkness, small, irregular bodies tumbling through tilted orbits. 2 new rings appeared, dark and narrow, composed of material so black it reflected barely any sunlight. The ring particles, scientists later determined, might be organic compounds, carbon-rich materials, unlike the bright ice rings of Saturn. Voyager's magnetometer detected that bizarre magnetic field, tilted and offset in ways that seemed impossible. Radio receivers heard crackling emissions, lightning-like discharges from deep in the atmosphere. Infrared sensors measured temperatures, confirmed the extreme cold, tracked how heat distributed across the planet's surface. For 6 hours, as Voyager swept past at more than 15 kilometers per second, every instrument ran at full capacity. Scientists on Earth received a flood of data, images and measurements that filled magnetic tapes, each byte traveling nearly 3 hours at light speed to reach home. And then Voyager was gone. Its trajectory carried it away from Uranus, diving below the orbital plane toward Neptune. The pale cyan disk shrank to a dot, then to nothing. Uranus returned to solitude. In all the decades since, no spacecraft has gone back. Voyager 2 remains the only machine to have seen Uranus up close, the only witness to its diamond storms and silent moons. The photographs it took, grainy and low resolution by modern standards, are still the best images we have. That data, stored on magnetic tapes that have been reanalyzed countless times, remains the foundation of everything we know about Uranus. And as the 2024 study showed, we're still discovering things hidden in those decades-old measurements. Voyager 2 is still out there, by the way, still flying. It crossed into interstellar space in 2018, the second human-made object to leave the solar system after Voyager 1. Its nuclear battery slowly decays, generating less power each year. Engineers have been shutting down instruments one by one to conserve energy for the communication systems. By 2035, maybe sooner, Voyager 2 will fall silent forever. Its transmitter will fade, its computers will sleep, but the spacecraft itself will continue coasting through the galaxy, a derelict messenger carrying a golden record with sounds and images from Earth, music, greetings in 55 languages, diagrams showing our While that hypothetical probe coasted silently through the dark, we transformed ourselves beyond recognition. That's the scale of interstellar distance, even to the nearest star, even traveling faster than any bullet. The journey takes longer than human civilization has existed. We are, for all practical purposes, trapped, confined to a tiny bubble around our sun by the tyranny of distance and the crawling pace of our fastest machines. But why? Why can't we just go faster, build a bigger rocket, use more fuel? Because physics has other ideas, and those ideas form walls we might never climb. Every rocket ever built obeys the same cruel mathematics. The faster you want to go, the more fuel you need. But fuel has mass. More mass means you need even more fuel to accelerate that fuel, which adds more mass, which requires more fuel still. The equation spirals into absurdity faster than most people realize. Konstantin Tsiolkovsky figured this out in 1897, decades before the first liquid-fueled rocket ever flew. He derived an equation so fundamental to spaceflight that it bears his name, the Tsiolkovsky rocket equation, and what it tells us is devastating. To reach just 10% of light speed, about 30,000 kilometers per second, using the best chemical rockets we have, you'd need more fuel than exists in all of Earth's oceans combined. That's not an exaggeration. That's what the math demands. Let me put that in perspective. The Saturn V rocket that carried humans to the moon stood 110 meters tall. Its total mass at launch was 2,170,000 kilograms. Of that mass, 2,190,000 kilograms was fuel, 94% fuel. Only 6% was actual rocket, payload, and crew capsule. And what did all that fuel achieve? A velocity of about 11 kilometers per second, enough to escape Earth's gravity and coast to the moon. Impressive by human standards, pathetic by cosmic ones. To reach Proxima Centauri in a reasonable time frame, say 100 years instead of 80,000, you'd need to travel at roughly 4,500 kilometers per second. That's 400 times faster than the Apollo missions. According to Tsiolkovsky's equation, achieving that speed with chemical propulsion would require a fuel mass so enormous that the numbers become meaningless. We're talking about ratios of trillions to one. Building a spacecraft where 99.99999% is fuel and a tiny fraction of a percent is actual payload, physically impossible. You'd run out of atoms in the observable universe before you had enough fuel, so chemical rockets are out. Combustion, the controlled explosion that's carried every mission from Sputnik to the International Space Station, simply cannot take us to the stars. The physics forbids it. What about ion drives? Surely those are more efficient. They are, dramatically so. Ion propulsion uses electricity to accelerate charged particles, typically xenon atoms, to extremely high velocities. Instead of burning fuel in a combustion chamber, an ion drive uses electric fields to strip electrons from atoms and then accelerate the resulting ions out the back of the spacecraft. The exhaust velocity of an ion drive can reach 30 to 40 kilometers per second, compared to about 4.5 kilometers per second for chemical rockets. That's nearly 10 times more efficient. With an ion drive, you get more thrust per kilogram of propellant. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. Over its mission lifetime, Dawn's ion engine changed the spacecraft's velocity by more than 11 kilometers per second, using only 425 kilograms of xenon propellant. If Dawn had used chemical rockets for those maneuvers, it would have required tons of fuel, so problem solved, right? Just use ion drives for interstellar missions. Not quite. Ion drives are efficient, but they produce minuscule thrust. Dawn's engine generated 90 millinewtons of force. That's the weight of 10 pennies pressing down on your hand. 10 pennies worth of thrust. It took Dawn days to make maneuvers that chemical rockets complete in seconds. To accelerate a spacecraft to interstellar velocities using ion propulsion would take millennia. And you'd still need a massive power source. Dawn used solar panels near Mars, where sunlight is relatively strong. Between stars, where darkness is absolute and the nearest sun is years away, solar panels become useless. You'd need a nuclear reactor, or an antimatter generator, or some other power source that doesn't currently exist. Every proposed solution runs into the same fundamental barrier: energy. Moving mass requires energy. The faster you want to move, the more energy you need, and energy must come from somewhere. Solar sails have been proposed as one elegant solution. Instead of carrying fuel, you unfurl enormous mirrors, kilometers across, and let photons from the sun push you. Sunlight has momentum, not much, but it's constant and free. Over years or decades, a solar sail could accelerate a lightweight probe to impressive speeds. The Planetary Society launched LightSail 2 in 2019, demonstrating that solar sailing works. The tiny spacecraft successfully raised its orbit using nothing but photon pressure from sunlight. Breakthrough Starshot, a privately funded initiative, proposes using ground-based lasers to propel postage stamp-sized spacecraft equipped with ultra-thin sails to 20% of light speed. 20%. That would get you to Proxima Centauri in about 20 years. Suddenly, interstellar travel doesn't seem quite so impossible, except for the engineering challenges. The sail would need to be incredibly thin, perhaps only a few atoms thick, to keep mass low. Even a speck of dust hitting the sail at 20% of light speed would release as much energy as a small bomb. The spacecraft would need to survive decades in the radiation-soaked interstellar medium, and once it arrived at Proxima, it would have no way to slow down. It would zip through the system at 60,000 kilometers per second, taking a few photographs before disappearing into the void beyond. Still, it's the closest thing to a feasible interstellar mission we currently have. Send thousands of these tiny probes, accept that most will fail, hope a few succeed, wait 20 years for data to trickle back at the speed of light. But what about crewed missions? Humans to another star system? Solar sails won't cut it. You can't send people on a postage stamp. Nuclear pulse propulsion offers one possibility. The concept is exactly as insane as it sounds. You detonate nuclear bombs behind your spacecraft, one after another, using the explosions to push a massive shock absorber plate that accelerates the ship forward. Project Orion, a serious engineering study conducted in the 1960s, concluded that nuclear pulse propulsion could work. The math checked out. A spacecraft propelled by sequential nuclear detonations could reach 5% of light speed, getting to Proxima in about 80 years. Still longer than a human lifetime, but approaching the realm of generation ships. The problems are obvious. First, you need thousands of nuclear bombs. Second, detonating them in atmosphere would violate every nuclear test ban treaty ever signed, and probably irradiate half a continent. Third, the engineering tolerances are absurd. The shock absorber would need to handle repeated nuclear blasts without failing, because a single failure means instant vaporization. And fourth, most importantly, nobody wants to build a spacecraft powered by nuclear bombs. The political and environmental obstacles make it a non-starter. Fusion drives offer a cleaner alternative. If we could harness the same nuclear reactions that power the sun, fusing hydrogen into helium and capturing the released energy, we'd have an almost ideal propulsion system. Fusion produces enormous energy from tiny amounts of fuel. A kilogram of fusion fuel contains millions of times more energy than a kilogram of chemical rocket fuel. The problem is we can't do it. Not yet. Despite decades of research and billions of dollars invested, controlled fusion remains just out of reach. Experimental reactors like ITER promise to achieve net positive energy from fusion sometime in the 2030s or 2040s. But those are massive facilities designed to generate electricity on Earth, miniaturizing fusion into something that fits on a spacecraft, while maintaining the extreme temperatures and pressures required for the reaction, is a completely different challenge. Even if we solve fusion, we're still talking about trips lasting decades or centuries. Fusion isn't magic, it's just a better fuel source. You're still limited by the amount of reaction mass you carry and how fast you can expel it. Antimatter represents the theoretical upper limit. When matter and antimatter meet, they annihilate, converting mass directly into energy according to Einstein's famous equation, E equals mc squared. Total conversion, 100% efficiency. No other energy source comes close. A single gram of antimatter reacting with a gram of matter releases energy equivalent to a 43 kiloton nuclear bomb, the explosive yield of the Hiroshima bomb from 2 grams of material. An antimatter rocket could theoretically reach 40% of light speed. Proxima Centauri in 10 years, Mars in hours, the outer solar system in days. Antimatter solves the fuel problem completely, except for one tiny detail. Antimatter doesn't exist naturally in any significant quantity. You have to make it, and making antimatter is outrageously expensive. CERN's particle accelerators can produce antiprotons, but at a rate of about 10 nanograms per year. At current production rates and costs, a single gram of antimatter would cost $62.5 trillion. That's trillion with a T. You'd need kilograms for an interstellar mission. We're talking about costs that exceed the entire economic output of human civilization, multiplied by hundreds or thousands. And even if cost weren't an issue, storing antimatter is phenomenally difficult. It can't touch normal matter, or it instantly annihilates. You need magnetic containment fields that can hold charged antimatter particles suspended in vacuum for years without a single failure. A power loss, a technical glitch, even a small magnetic fluctuation, and your fuel explodes with nuclear force. Every propulsion system we can imagine runs into insurmountable obstacles. Chemical rockets lack efficiency, ion drives lack power, solar sails lack control, nuclear pulse propulsion lacks political viability, fusion lacks technological readiness, antimatter lacks affordability and safety. We're trapped by the tyranny of the rocket equation and the laws of thermodynamics. Moving fast requires energy. Energy requires fuel. Fuel has mass. Mass requires more fuel. The spiral never ends. But perhaps we're thinking about this wrong. Perhaps the problem isn't the fuel or the engine. Perhaps the problem is trying to move mass at all. What if you could manipulate space-time itself? Bend it, fold it, create shortcuts through the fabric of reality. Scientists have explored these ideas seriously. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a mechanism for faster-than-light travel that doesn't actually violate relativity. Instead of moving through space, you contract space in front of your ship and expand it behind. You surf a wave of warped space-time, remaining stationary relative to your local space while that space moves faster than light. The math works. General relativity permits such solutions. There's no law of physics that explicitly forbids the Alcubierre drive. The catch? You'd need exotic matter with negative mass energy, and lots of it. Initial calculations suggested you'd need more negative energy than exists in the observable universe. Later refinements reduced that to merely Jupiter's mass worth of exotic matter. Exotic matter, to be clear, has never been observed. We have no idea if it exists. We have no idea how to make it. And even if it does exist somewhere in the universe, we certainly can't harvest Jupiter masses of it. Wormholes offer another theoretical shortcut. Einstein's equations allow for tunnels through space-time connecting distant points. Jump in one end, emerge instantly at the other. No travel time, no distance, just a doorway from one part of the universe to another. Again, the equations work. Wormholes are mathematically valid solutions to general relativity. The problem is stability. Natural wormholes, if they exist, collapse immediately. To keep a wormhole open long enough to travel through, you'd need, once again, exotic matter, negative energy to prop open the tunnel and prevent it from pinching shut. Quantum tunneling, warp drives, wormholes, every shortcut proposed by theoretical physics requires either exotic matter we can't produce, energy densities we can't achieve, or both. We're back where we started, trapped, confined to our tiny corner of the galaxy by the stubborn persistence of physics. 80,000 years to Proxima Centauri at Voyager's speed. That's 4,000 human generations. If your ancestors had launched a probe toward Proxima in the Stone Age, it would arrive today, and they would have needed technology we only developed in the 20th century. Think about what that means for any real interstellar mission. You launch a ship. Your great-great-great-grandchildren might see data return, maybe, if nothing fails during the journey. If humanity still exists when the signal arrives, if anyone remembers why the mission launched in the first place. Carl Sagan once said that in order to make an apple pie from scratch, you must first invent the universe. In order to reach another star, you must first solve problems that may not have solutions, create materials that may not exist, generate energy from sources we haven't discovered, and convince a civilization to invest resources in a mission whose benefits won't be realized for thousands of years. The universe has given us the ability to see the stars, to measure their distances, analyze their spectra, detect their planets. We can observe worlds orbiting other suns with exquisite precision. We know their masses, their compositions, their temperatures. We can calculate which ones might harbor life. But the same universe that lets us see those worlds has locked them behind barriers we may never cross. 40 trillion kilometers of empty space, the speed of light as an ultimate limit, the rocket equation as a hard constraint on motion. We're like prisoners in the most beautiful cell imaginable, able to see infinite wonders through the bars but unable to touch them. The cosmos dangles paradise just out of reach and then reminds us, with cold mathematical certainty, that reaching is futile. Yet we keep trying. We design missions. We calculate trajectories. We dream of technologies that don't exist yet. Because somewhere in human nature lives the refusal to accept impossibility. And maybe, just maybe, that refusal is enough. Not to break the laws of physics, but to find the loopholes we haven't noticed yet. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would fundamentally reshape our understanding of reality. Albert Einstein's special theory of relativity introduced a concept so counterintuitive, so deeply weird, that even today most people struggle to fully grasp its implications. Nothing with mass can reach the speed of light, ever, under any circumstances. The universe has built this restriction into the very fabric of space-time, and there are no exceptions. You might think that's just an engineering problem. Build a more powerful engine, add more fuel, accelerate harder. Eventually you'll get there, right? But the universe doesn't care about your engineering. As you approach light speed, something profoundly strange happens. You get heavier. Every particle in your spacecraft, every atom in your body, every photon of energy in your fuel cells gains mass as velocity increases. At 90% of light speed, your mass has increased by a factor of 2.3. You're more than twice as heavy as when you started, and you haven't added a single atom of material. At 99% of light speed, your mass multiplies by 7. At 99.9%, you're 22 times heavier than your rest mass. The closer you get to light speed, the more mass you gain, and the more energy required to accelerate further. By the time you reach 99.9999% of light speed, your mass has grown so enormous that accelerating even 1 more meter per second requires energy equivalent to the output of stars. And you're still not there. You're still crawling below the ultimate speed limit. At exactly the speed of light, your mass becomes infinite. The energy required to accelerate you, that final infinitesimal amount, also becomes infinite. You would need to harness the energy of the entire universe just to push one atom across that threshold. The mathematics are brutally clear. The Lorentz factor, the equation that describes how mass increases with velocity, approaches infinity as velocity approaches light speed. You're not fighting engineering limitations. You're fighting a mathematical singularity, an asymptotic barrier that gets steeper the closer you approach it. Light itself can only travel at light speed because photons have no rest mass. Zero mass means the Lorentz factor doesn't apply. Photons are born moving at 299,792 kilometers per second and can never slow down or speed up. They exist only at that precise velocity, forever. Anything with mass lives on the other side of that barrier, forever slower than light, forever trapped below that cosmic speed limit. Einstein didn't impose this limit arbitrarily. He derived it from observations about how the universe actually works. The speed of light appears the same to all observers regardless of their motion. That simple fact, confirmed by countless experiments, leads inevitably to all the weirdness of relativity. And it means that the gap between us and Proxima Centauri isn't just 4 light years of empty space. It's 4 years minimum travel time, even if you could somehow reach light speed, which you can't. So the real travel time is much, much longer. But let's say we solve the engineering problems. Let's say we develop a propulsion system so advanced, so efficient, so utterly beyond our current capabilities that we can accelerate a spacecraft to 99.9% of light speed, not quite reaching the barrier, but getting devastatingly close. At that speed, you could reach Proxima Centauri in about 4.5 years. Ship time. You board the spacecraft, spend 4.5 years in transit, and arrive at another star system. From your perspective, the journey is shorter than a college degree program. But here's where relativity reveals its cruelest trick: time dilation. When you move at relativistic speeds, time itself slows down for you relative to the rest of the universe. The faster you move, the slower your clock ticks compared to clocks back on Earth. This isn't an illusion or a measurement error. Time genuinely passes at different rates depending on your velocity. At 99.9% of light speed, time dilation becomes extreme. For every year that passes on your spacecraft, 22 years pass on Earth. Your 4.5-year journey to Proxima? Back home, 99 years have elapsed, nearly a century. Everyone you knew is dead. Your children are elderly. Your grandchildren have grandchildren. The world you left no longer exists. Language has evolved. Technology has advanced. The political landscape is unrecognizable. You return younger than your descendants, a ghost from the past appearing in an alien future. And that's assuming you return at all. Reaching Proxima at 99.9% of light speed means another 4.5 years ship time for the return journey. But Earth, another 99 years. You've been gone for 9 years subjectively. Earth has aged 2 centuries. The civilization that built your spacecraft might not even exist anymore. The people waiting for your signal might have forgotten you launched. Your mission could return to a planet where nobody remembers why you left. This is the paradox at the heart of relativistic travel. Speed gives you the ability to cross cosmic distances within a human lifetime, but only your lifetime. Everyone else ages normally. The faster you go, the farther forward in time you jump with each journey. You could theoretically circumnavigate the entire galaxy in a single lifetime if you traveled close enough to light speed. From your perspective, subjective decades would pass. But when you return to Earth, millions of years would have gone by. Our sun would have changed. Our planet might be unrecognizable. Humanity itself might be extinct or evolved into something unrecognizable. You become unstuck in time, a traveler between eras rather than places. Twin paradox experiments have confirmed this effect. Place an atomic clock on a jet aircraft, fly it around the world, and when it lands, the clock has fallen behind Earth-based clocks by nanoseconds. Those nanoseconds prove time dilation is real. At jet speeds, the effect is tiny. At relativistic speeds, it becomes overwhelming. Mons, subatomic particles created when cosmic rays hit the upper atmosphere, demonstrate this beautifully. Mons decay in about 2 microseconds. At the speed they travel after being created, they shouldn't be able to reach Earth's surface before decaying. The distance is too great, yet muon detectors at ground level register them constantly. Why? Because from the muon's perspective, time has slowed down. Those 2 microseconds stretch into enough time to complete the journey. From our perspective, the muons are moving so fast that time dilation extends their lifespan long enough to reach the surface before decaying. We've measured this. We've confirmed it. Time dilation is as real as gravity. So here's the nightmare scenario for interstellar exploration. You assemble a crew, young people, brilliant minds, willing to sacrifice everything for the chance to see another world. You launch them toward Proxima Centauri at the highest speed your technology allows. They spend years in transit, training, conducting experiments, living together in a metal can hurtling through the void. They arrive at Proxima, gather data, take measurements, maybe even land on Proxima b if conditions allow. Then they turn around and come home. The journey back takes just as long as the journey out. From their perspective, maybe 15 or 20 years have passed. They've aged normally. They remember their families, their training, the world they left. They arrive back at Earth orbit expecting a hero's welcome, expecting to be debriefed, to share their discoveries, to tell their stories to a grateful planet. Instead, they find that 4 centuries have passed. Everyone they knew is long dead. The technology that launched them is ancient history. Their spacecraft is a primitive relic. The data they gathered has been superseded by advances in telescopes and quantum sensors that can observe Proxima b in exquisite detail without sending ships. Their entire mission was rendered obsolete before they even arrived at Proxima. Faster technologies were developed while they were in transit. Other missions using better propulsion arrived at Proxima, completed their studies, and returned home while the first crew was still en route. The crew becomes a historical curiosity, brave pioneers who sacrificed everything for a mission that nobody needed anymore, time travelers who wagered their lives on a journey that lost relevance before it could be completed, and you can't warn them. Radio signals travel at light speed. If you send a message telling them to turn around, by the time it reaches them, they might already be decelerating into Proxima's system. The transmission delay makes communication meaningless. Every conversation spans years. Every question takes years to answer. You're not exchanging information with them. You're sending messages in bottles that will wash ashore long after the moment has passed. This is the fundamental cruelty of relativistic travel. The faster you go, the more you orphan yourself from your own timeline. You trade distance for belonging. You can reach the stars, but you can never come home. Some physicists have suggested using this property intentionally. Want to see the far future? Just accelerate to near light speed and coast. Each decade of your subjective time could be centuries or millennia of objective time. You could witness the evolution of civilizations, the birth and death of empires, the transformation of species, all while barely aging. But you'd be completely alone, a perpetual outsider watching history through a window you can never open. Every person you meet would be a temporary connection soon lost to the river of time flowing past you. So when we talk about reaching Proxima Centauri, we're not just talking about crossing 40 trillion kilometers. We're talking about choosing between 2 prisons. Stay on Earth and remain trapped by distance, unable to reach the nearest star, or achieve near light speed and become trapped outside of time itself, able to reach anywhere but never able to truly belong. The universe gives us the stars but makes them unreachable, or it gives us speed but takes away our place in history. The light barrier stands before us like a wall, written in the language of mathematics. On one side, everything we've ever known, our solar system, our slow spacecraft, our reasonable travel times between planets. On the other side, the vast majority of the universe, trillions of stars, billions of potentially habitable worlds, entire galaxies full of wonders we will never see. And separating these 2 realms is a line we cannot cross, not because we lack the engineering skill, not because we haven't discovered the right fuel or the right propulsion system, but because the universe itself says no. Einstein's equations are laws, not suggestions. They describe how reality operates at the deepest level. Violating them would require breaking the fundamental structure of space-time itself. But what if we could do exactly that? What if instead of trying to move faster through space, we move space itself? What if we found a way to bend the rules without actually breaking them? This brings us back to the Alcubierre drive, the warp bubble concept that Miguel Alcubierre proposed in 1994, a solution to Einstein's field equations that allows for apparent faster-than-light travel by manipulating space-time geometry. The idea is elegant. Space itself can expand and contract. We see this happening throughout the universe. Galaxies are moving away from us, carried by the expansion of space, some of them receding faster than light. The speed limit applies to objects moving through space, not to space itself expanding. Alcubierre asked a simple question. What if we could create controlled expansion and contraction, compress space in front of a spacecraft and expand it behind? You'd create a wave of space-time, and the spacecraft would surf that wave. From the outside, the spacecraft would appear to move faster than light. But from the crew's perspective, they're not moving at all. They're stationary inside a bubble of flat space-time being carried along by the wave. Local physics remains normal. No time dilation, no mass increase, no violation of special relativity. The math works. The equations balance. There's no explicit law of physics that forbids the Alcubierre drive. The problem, creating the warp bubble requires negative energy, enormous amounts of it. Energy with properties opposite to normal matter. Energy that pushes instead of pulls. Energy that, as far as we know, doesn't exist in any usable form. Initial calculations suggested you'd need negative energy equivalent to the mass of Jupiter. Later refinements reduced that to merely the mass of Voyager 1. Still an impossible requirement, but at least mathematically approachable. Even if negative energy exists, and we figure out how to generate it, we face other problems. The front of the warp bubble would accumulate particles from space. Upon arrival at your destination, releasing the bubble might unleash those particles as a devastating radiation blast, capable of sterilizing planets. There's also the causality problem. Faster-than-light travel of any kind potentially allows for time travel paradoxes. Going faster than light in one reference frame means going backward in time in another. You could theoretically arrive before you departed, creating closed time-like curves and all the paradoxes that implies. The universe might have safeguards against this. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics conspire to prevent closed time-like curves. Whenever you try to create conditions for backward time travel, quantum effects intervene and destroy the mechanism. Maybe negative energy can't exist in sufficient quantities. Maybe warp bubbles are inherently unstable. Maybe the universe closes these loopholes at scales we can't yet calculate. Or maybe, just maybe, we haven't been clever enough yet. Maybe the solution exists and we simply haven't found it. But until we do, the light barrier remains absolute. The distance to Proxima Centauri remains insurmountable, and time dilation remains the price of speed. We're left staring at the stars, close enough to see but forever just out of reach, trapped in our tiny bubble around the sun, imprisoned by physics itself. And yet 4.24 light-years away, a red dwarf star continues to burn. Around it, a rocky planet circles in the habitable zone, and we continue to dream about reaching it. 4.24 light-years away, across an ocean of darkness that has never known sound or warmth or touch, burns a star so dim you cannot see it with your naked eye. Proxima Centauri, our nearest stellar neighbor, the closest sun to our sun, and yet invisible to human vision despite being closer than any other star in the night sky. Stand outside tonight and look up. Every star you see, every pinpoint of light scattered across the darkness, is farther away than Proxima. Yet you won't find it. Your eyes aren't sensitive enough. The star produces too little light. Its glow is too faint, too red, too weak to register on human retinas designed to see the bright yellow-white light of our own sun. You need a telescope to find Proxima, a good one. And even then, you're looking at a dim crimson ember, a smoldering coal compared to the blazing furnace we orbit. If our sun were a lighthouse, Proxima would be a candle flame guttering in fog. Red dwarfs like Proxima are the universe's most common stars. They make up 70% of all stars in the Milky Way. Small, cool, efficient, burning hydrogen so slowly that they'll outlive every other type of star by orders of magnitude. Our sun has perhaps 5 billion years left before it swells into a red giant and consumes the inner planets. Proxima Centauri will still be burning trillions of years from now, long after our sun is a cold white dwarf, long after every massive star has exploded or collapsed into a black hole. Red dwarfs are the cockroaches of the cosmos, small, resilient, impossible to kill. They'll be the last lights burning when the universe grows old and dark. Proxima has only 12% of our sun's mass, 8 times less massive than the star that gave us life. If you could somehow transport Proxima into our solar system and place it where the sun currently sits, Earth would freeze solid within weeks. The temperature would plunge to levels where the atmosphere itself would condense and fall as snow. Nitrogen snow, oxygen snow, the building blocks of our air crystallizing into icy flakes that bury continents. Yet Proxima has a planet, Proxima b, discovered in 2016 after years of careful observation, watching the star wobble minutely as the planet's gravity tugged it back and forth. The radial velocity method, detecting the Doppler shift in starlight caused by a planet's orbital dance. Proxima b orbits its star every 11.2 days. 11 days, that's how long it takes to complete one full orbit. Earth takes 365 days. Mercury, our innermost planet, takes 88 days. Proxima b circles its sun faster than any planet in our solar system, and it's close, astonishingly close. The planet orbits at a distance of just 7.5 million kilometers from Proxima. For comparison, Earth sits 150 million kilometers from our sun. Proxima b is 20 times closer to its star than we are to ours. At that distance, you might expect the planet to be a scorched hellscape, baked by radiation and stellar heat. But Proxima is so dim, so cool, that even this close proximity puts the planet right in the habitable zone, the Goldilocks region where temperatures allow liquid water to exist on the surface. Liquid water, the single most important ingredient for life as we know it, and Proxima b might have it. But there's a cost to orbiting that close to a star. Tidal locking. The same gravitational forces that locked our moon to always show Earth the same face have locked Proxima b to always show Proxima Centauri the same hemisphere. One side of the planet eternally faces the star, baking under constant radiation. The other side faces away forever, frozen in perpetual night. Imagine living on a world where the sun never moves. Stand on the day side and Proxima hangs overhead, enormous and red, fixed in the sky like a baleful eye. It never rises, never sets, just burns there, hour after hour, year after year, century after century. The landscape beneath that eternal star would be a desert of rock and possibly evaporated ocean, temperatures soaring beyond habitability. Walk to the other hemisphere and you enter endless darkness. The sun never appears. Stars wheel overhead in their slow procession, but the star that warms your world remains forever hidden beyond the horizon. Temperatures plunge to cryogenic cold. Any water that exists here is locked in ice kilometers thick. Between these two extremes lies the terminator, the twilight zone, a narrow band circling the planet where day and night meet but never fully become either. Here, the sun sits permanently on the horizon, half risen, half set, creating an endless sunset that stretches around the entire planet like a ring. This is where life might exist, if it exists at all, in the perpetual dusk, where temperatures moderate, where liquid water could pool in lakes and rivers, fed by ice melting on the night side and condensing from evaporation on the day side. Scientists have run climate models of tidally locked planets. The results are strange but not impossible. Thick atmospheres could redistribute heat, preventing the day side from becoming too hot and the night side from freezing solid. Winds would howl constantly, driven by the temperature differential, circulating warm air toward the frozen night and cool air toward the scorching day. If you stood in the terminator zone of Proxima b, you'd experience perpetual storms, winds that never cease, clouds racing overhead, lit from below by the red star always sitting on the horizon. The sky wouldn't be blue. Red dwarf starlight lacks the wavelengths that create Earth's azure dome. Instead, you'd see deep crimson and purple, shades of twilight that never brighten to day or darken to full night. And the star itself would appear huge, 3 times larger in the sky than our sun appears from Earth, because you're so much closer. A swollen red orb dominating the horizon, its surface possibly mottled with sunspots and flares visible to the naked eye. Because Proxima is violent, deceptively so. Red dwarfs might burn slowly and live long, but they're temperamental in their youth and middle age. Stellar flares erupt from their surfaces with terrifying frequency, especially for small red dwarfs like Proxima. In 2016, the same year Proxima b was discovered, astronomers observed a massive flare from Proxima Centauri. The star's brightness increased by nearly 20% in just 10 seconds. Then it faded back to normal. The flare released as much energy as 1 million hydrogen bombs detonating simultaneously. For the 11 minutes that flare burned, Proxima b was bathed in radiation equivalent to standing outside during a nuclear explosion. X-rays, ultraviolet light, charged particles accelerated to relativistic speeds. Any life on the surface would have been flash-fried unless it had protection. Thick atmosphere, underground shelters, water covering, something to block the deadly radiation. And flares like this happen regularly. Multiple times per year, sometimes multiple times per month. Proxima is still magnetically active, generating powerful magnetic fields that twist and snap, releasing stored energy in violent bursts. Over billions of years, these flares have likely stripped away much of Proxima b's original atmosphere, if it had one. The planet might have started with air as thick as Earth's, but stellar wind and radiation could have eroded it, blowing atmosphere into space atom by atom until only a thin shell remains. Or maybe not. Maybe Proxima b is large enough and geologically active enough to replenish its atmosphere faster than flares strip it away. Maybe volcanic activity releases gases that replace what's lost. Maybe the planet had so much water that even after billions of years of bombardment, enough remains to sustain an ocean. We don't know. And that uncertainty drives scientists absolutely wild, because Proxima b isn't just any exoplanet. It's the closest exoplanet to Earth, the only one within even theoretical reach of our current or near-future technology. If we're going to study an alien world in detail, if we're going to search for signs of life beyond our solar system using anything other than telescopes, Proxima b is the only realistic target. Enter the James Webb Space Telescope, the most powerful astronomical instrument ever built. Launched in 2021, positioned at the L2 Lagrange point 1.5 million kilometers from Earth, Webb can detect infrared light with unprecedented sensitivity. It can analyze the atmospheres of distant exoplanets by watching them pass in front of their stars and measuring how starlight filters through their air. Except Proxima b doesn't transit. From our viewing angle, the planet doesn't pass between us and its star. We see the system from an oblique angle, which is why the planet was discovered through radial velocity rather than the transit method. Webb can't use its most powerful technique for atmospheric analysis. But that doesn't mean Webb is useless. In 2022 and 2023, astronomers used Webb to observe Proxima b directly, searching for thermal emission from the planet itself. The results remain inconclusive. The observations are difficult. Proxima Centauri is so close to Proxima b in our sky that separating the planet's faint glow from the star's overwhelming light is like trying to see a firefly next to a searchlight. Initial data hints at something, possibly a thick atmosphere, possibly water vapor, possibly methane, or possibly just noise in the measurements, artifacts of observational limitations rather than real signals from an alien world. Further observations are planned. More time on Webb, refinements to data processing. Maybe in a few years we'll have definitive answers about Proxima b's atmosphere. Maybe we'll detect oxygen or methane or other biosignature gases that could indicate life. Or maybe we'll find that Proxima b is airless, stripped bare by its star's violence, a rocky ball orbiting too close to a temperamental sun that never gave life a chance to begin. The irony is profound. The nearest star to our sun is hostile. The nearest potentially habitable planet orbits in conditions that seem designed to make life as difficult as possible. Constant radiation, tidal locking, atmospheric erosion, stellar flares that would sterilize any surface life that tried to establish itself. And yet life on Earth thrives in places we once thought impossible. Extremophiles living in boiling hydrothermal vents, bacteria surviving in Antarctic ice, microbes dormant in salt crystals for millions of years, reviving when water returns, organisms that feed on radiation, on sulfur, on chemicals we consider toxic. Life adapts, life persists, life finds a way in environments that seem utterly inhospitable. Maybe Proxima b hosts organisms that evolved to withstand radiation we'd consider lethal. Maybe they shelter underground, in caves or beneath oceans, emerging only during lulls between flares. Maybe they have biological mechanisms to repair radiation damage faster than it accumulates. Or maybe life there never evolved past simple chemistry. Maybe the conditions are just hostile enough to prevent the complex chain reactions that lead from molecules to cells to organisms. Maybe Proxima b represents the edge of habitability, a world where life almost happened but couldn't quite overcome the barriers. Either way, we won't know until we get there. And getting there requires crossing 40 trillion kilometers of absolute emptiness. 40 trillion, a number so large it becomes abstract. If you started driving toward Proxima Centauri at highway speed, maintaining a constant 100 kilometers per hour without stopping, you'd arrive in 45 million years. 45 million years ago, the first grasses were evolving on Earth. The ancestors of horses were the size of dogs. Antarctica was warmer than it is now. Humans didn't exist. Primates barely existed. That's the timescale required to drive to the nearest star at highway speeds. The entire history of human evolution is shorter than the drive to Proxima. If Earth were a grain of sand, Proxima would be another grain of sand on the other side of North America. Everything between them would be empty air, no planets, no asteroids, no dust, just void so complete that you could fit 1 billion solar systems in the gap and they wouldn't come close to filling it. The space between stars isn't just distance, it's isolation raised to a level we can barely comprehend. It's loneliness on a cosmic scale. It's the universe reminding us that stars are islands, separated by oceans of nothing. And yet across that impossible gap, we can see Proxima. We can measure its light. We can detect its planet. We can study its flares and calculate its age and determine its composition. Light carries information across the void, and we've learned to read that information with exquisite precision. We know more about Proxima Centauri, a star we'll likely never reach, than ancient humans knew about their own planet. We've mapped its surface features. We've clocked its rotation period at 83 days. We've measured its magnetic field strength and tracked its stellar activity cycles. And we know it has at least one planet, possibly more, circling in its faint red light. Worlds that might hold water, maybe life, maybe the answer to whether we're alone in the universe. But knowing and reaching are separated by a chasm that physics itself may forbid us from crossing. We can see paradise, we can study it, we can dream about it, but touching it, walking on its surface, breathing its air if it has any, might be forever beyond our grasp. Proxima b sits there, 4 light-years away, neither confirming nor denying the possibility of life, teasing us with its location in the habitable zone, taunting us with its proximity, which is still impossibly far. And beyond Proxima, beyond this nearest stellar island, lie hundreds of billions of other stars in our galaxy alone, each one potentially hosting planets. Some of those planets certainly in habitable zones, some percentage of those almost certainly hosting life. The galaxy is probably teeming with it. Microbes on countless worlds, maybe complex organisms, maybe intelligence, maybe civilizations that solve the problems of interstellar travel and spread among the stars like seeds on the wind. But if they exist, they're separated from us by voids we cannot cross. And if we exist surrounded by life, we're alone anyway, trapped in our solar system by the tyranny of distance and the hard limits of physics. So we point our telescopes at Proxima b. We gather data, we build models, we speculate about atmospheres and oceans and organisms we've never seen and may never encounter. And we continue searching for ways to break the barriers that confine us. Because somewhere in human nature lives an unshakable belief that impossible just means we haven't figured it out yet. Between our sun and Proxima Centauri lies something that defies every human instinct about space. We call it the interstellar medium, which sounds official and scientific, but really we should call it what it is: the most perfect vacuum nature has ever created, the most absolute emptiness that physics allows to exist. Most people think of space as empty, the void between planets, the darkness beyond Earth's atmosphere, but that space is crowded compared to the interstellar medium. Between Earth and Mars, there are still particles, solar wind streaming from our sun, cosmic dust drifting on magnetic fields, occasional asteroids, the entire asteroid belt occupying the gap between Mars and Jupiter. Space in our solar system has texture, density, things happening. The interstellar medium has almost nothing. On average, you might find 1 atom per cubic centimeter. In a volume the size of a sugar cube, a single hydrogen atom drifts alone. For comparison, the air you're breathing right now contains roughly 10 to the power of 19 molecules per cubic centimeter. 10 quintillion molecules in a sugar cube of air. The interstellar medium has 1 atom in that same volume. Take all the air from a room, pump it out until you've created the best vacuum Earth-based technology can achieve. You'd still have billions of atoms per cubic centimeter. The interstellar medium is 1,000,000 times more empty than the best vacuum we can create in laboratories. And this emptiness extends for light years, 4.24 light years from here to Proxima, 40 trillion kilometers of almost nothing. A void so complete that if you released a puff of air into it, the molecules would drift apart and never find each other again. Each atom would become its own isolated system, traveling through darkness for millions of years before encountering anything else. Yet even this near-perfect vacuum isn't truly empty. Those rare atoms, mostly hydrogen with traces of helium and heavier elements, carry information about the history of the galaxy. Some are pristine material left over from the Big Bang, hydrogen that's never been inside a star. Others are recycled, forged in stellar cores and expelled when stars died. Carbon, oxygen, nitrogen, the building blocks of life itself, scattered atom by atom through the void. Magnetic fields thread through this emptiness, invisible lines of force generated by galactic currents and stellar winds. Cosmic rays zip through the darkness, particles accelerated to near light speed by supernova explosions that happened thousands or millions of years ago. They travel from galaxy to galaxy, crossing voids that would take light centuries to traverse, carrying energy that could fry electronics or damage DNA. And there's dust. Not dust as we know it, not the accumulation of dead skin cells and fabric fibers that settles on furniture. Interstellar dust consists of particles smaller than the wavelength of visible light, grains of silicates and carbon compounds drifting between the stars. Over distances of light years, even this sparse dusting of material becomes significant, blocking starlight and creating the dark nebulae visible in photographs of the Milky Way. A spacecraft traveling to Proxima would encounter all of this. Every atom, every cosmic ray, every dust grain. At low speeds, these encounters mean nothing. Voyager 2 has been traveling through the interstellar medium since 2018, and while it detects the change in environment, the impacts are negligible. At 55,000 kilometers per hour, hitting a dust grain is like getting hit by a snowflake while walking. But at relativistic speeds, everything changes. At 20% of light speed, a proposed velocity for breakthrough starshot probes, every atom becomes a bullet. Every dust grain becomes a bomb. The kinetic energy of impact scales with the square of velocity. Double your speed and impacts release 4 times more energy. Go 10 times faster, and impacts release 100 times more energy. At 20% of light speed, roughly 60,000 kilometers per second, collision with a single hydrogen atom releases energy equivalent to the atom's mass multiplied by the square of that velocity. The numbers work out to about 30 electron volts per atom, individually trivial, but you're hitting 1 trillion atoms per second even in the sparse interstellar medium. The accumulated energy becomes ionizing radiation, degrading materials, and damaging any electronics on board. Dust grains are worse, much worse. A grain the size of a bacterium, just a few microns across, hitting your spacecraft at 20% of light speed releases energy comparable to a bullet. It could punch through solar sails, damage sensors, or destroy crucial components, and you have no way to shield against it. Armor thick enough to stop these impacts would make your spacecraft too heavy to accelerate. Some proposed solutions involve clouds of gas surrounding the spacecraft, ablative shields that vaporize as they absorb impacts. Others suggest magnetic fields that deflect charged particles before they hit. But dust grains are neutral. Magnetic fields can't touch them, and any shield system adds mass, which reduces your top speed, which increases travel time, which exposes you to more impacts. You're damned if you do and damned if you don't. Go slow, and the journey takes millennia. Go fast, and the interstellar medium becomes a sand-blasting wind that erodes your spacecraft atom by atom. Even assuming you solve the propulsion problem, even assuming you achieve speeds that make the journey possible within human timeframes, you still have to survive the crossing. And survival depends on engineering that doesn't exist yet, materials that can withstand continuous bombardment, power systems that last for decades without maintenance, computer systems that can operate in environments saturated with cosmic radiation. Every component must be redundant. Every critical system must have backups for its backups. Because once you're in the interstellar medium, there's no possibility of rescue, no way to send replacement parts, no option for turning around if something breaks. The spacecraft continues on its trajectory, functional or not, until it either reaches its destination or drifts forever as a derelict. The psychological weight of this isolation would be staggering for any crewed mission. Imagine boarding a spacecraft knowing you'll spend decades, possibly your entire life, in a metal cylinder with the same handful of people. No sunrises, no weather, no seasons, except those artificially created by life support systems. The Earth behind you, visible through a telescope as a pale blue dot that shrinks and fades as you travel farther. Eventually it becomes just another star, indistinguishable from countless others. Your children would be born in transit. They'd grow up never seeing a horizon, never feeling rain, never breathing air that wasn't recycled. Their entire world would be corridors and compartments, hydroponic gardens, and exercise modules. They'd learn about Earth from videos and stories, but it would be as alien to them as Mars is to us now. And they'd know they're going to die before arriving. Their children would die. Their grandchildren would die. Generation after generation living and dying aboard the same vessel, traveling toward a destination none of them will see. Only their descendants, perhaps 100 generations removed from the original crew, would finally orbit Proxima Centauri and look upon an alien world. This concept has a name: generation ship. Self-contained worlds traveling between the stars, carrying populations large enough to maintain genetic diversity and cultural continuity across centuries. Science fiction has explored the idea extensively. Novels like Rendezvous with Rama, Aurora, and The Forever War grapple with the social and psychological challenges of multi-generational voyages. The engineering challenges are staggering. You'd need to create a stable ecosystem, perfectly balanced between oxygen production and carbon dioxide consumption, waste recycling and food production. Any imbalance that accumulated over decades would spell disaster. Run short of water and there's no resupply. Lose too much atmosphere to leaks and you can't manufacture more from nothing. Social stability presents even greater challenges. How do you maintain cohesion in a society that knows they're sacrificing everything for a goal they'll never see? What happens when a generation decides the mission isn't worth it and wants to turn back? Or worse, when different factions within the ship develop conflicting goals? There's nowhere to go if society fractures. No separation possible. Everyone is trapped together until journey's end. Studies of isolated communities suggest that populations smaller than several thousand people face genetic bottlenecks and cultural drift that could undermine the mission. You'd need tens of thousands of people to maintain diversity and skills across generations, which means building a spacecraft the size of a small city, which means launching a mass so enormous that no rocket could possibly accelerate it to meaningful speeds. The numbers spiral into impossibility faster than you can calculate them. Every solution creates new problems. Every answer raises 10 new questions. Yet we keep designing these missions. Project Daedalus in the 1970s proposed a fusion-powered unmanned probe that could reach Barnard's star in about 50 years. Project Longshot in the 1980s refined the concept, adding reconnaissance capabilities and better fuel management. Breakthrough Starshot in the 2010s pivoted to laser-propelled nanosatellites, accepting that we can't send humans, but maybe we can send sensors. Each generation takes the impossible dream of the previous generation and tries to make it slightly less impossible. We're slowly, incrementally, working through the problem space, eliminating approaches that definitely won't work and refining concepts that might. In 2016, Stephen Hawking and Yuri Milner announced Breakthrough Starshot with considerable fanfare. The concept seemed almost feasible. Build thousands of tiny spacecraft, each one weighing less than a gram. Equip them with ultra-thin light sails. Use a ground-based laser array to accelerate them to 20% of light speed. Send them toward Proxima Centauri. 20 years later, they arrive, take photographs, gather data, and transmit it back to Earth. Another 4 years for the radio signal to return. Total mission time from launch to data reception, 24 years. For the first time, interstellar exploration seemed achievable within a human lifetime. Not sending people, but sending eyes and sensors. Enough to tell us if Proxima b has an atmosphere, if there's water, if there might be life. The technical challenges remain formidable. The laser array would need to output 100 gigawatts, roughly the power consumption of a small country, focused into a beam precise enough to push postage stamp-size sails thousands of kilometers away. The spacecraft would need to survive decades in space with no maintenance, then function perfectly on arrival despite radiation damage. The communication system would need to transmit data across 4 light-years using a laser powered by a sail-sized collector, hoping someone on Earth is listening when the signal arrives, and you'd launch thousands of them, accepting that most will fail. Some will tumble and lose their orientation. Others will be hit by dust grains and destroyed. A few will suffer electronic failures or lose power. But if even 1% succeed, if 10 or 20 spacecraft make it to Proxima and send back data, the mission succeeds. This is the calculus of interstellar exploration in our current era. Not grand adventures with crews of explorers, but swarms of disposable probes, launched in volume, accepting massive failure rates, hoping a handful survive to tell us what's out there. It's inglorious, unromantic, far removed from the visions of gleaming starships that science fiction promised us. But it might actually work. With technology we could develop in the next few decades, we might genuinely send probes to another star system and receive data back before the children born today retire. That's assuming we solve the laser problem, and the sail problem, and the navigation problem, and the communication problem, and fund the project despite costs measured in billions, and maintain the receiving infrastructure for the 24 years between launch and data return, and avoid any political or economic catastrophes that terminate funding mid-mission. Lots of assumptions, but fewer than generation ships require, fewer than fusion rockets or antimatter drives or any other crude mission concept. Proxima Centauri might remain forever beyond our physical reach, but maybe, just maybe, we can send our eyes there, send our sensors, send machines that carry no names or nationalities, just the accumulated knowledge of a species that looked at the stars and refused to accept that distance meant defeat. And if those machines arrive, if they turn their cameras toward Proxima b and transmit images back across the void, we'll see what no human eye has ever witnessed. An alien world in another star system, a place where the sun is red and small, and the sky glows in colors Earth never knew. That data, those images, would transform human civilization. Proof that we can reach beyond our solar system. Evidence that the barriers aren't absolute. Confirmation that distance can be crossed, even if not by humans. And perhaps that's enough. Perhaps knowing is enough. Perhaps we don't need to walk on Proxima b to understand it. Perhaps sending our machines, our instruments, our curiosity in digital form suffices, or perhaps it doesn't. Perhaps the dream of humans standing on alien soil, breathing air from another world, looking up at an unfamiliar sky, remains essential to who we are. Perhaps machines can explore, but humans must experience. The tension between these perspectives defines our relationship with interstellar space, the desire to reach versus the acceptance that reaching might be impossible, the dream of expansion versus the reality of physics. And at the center of it all, 4 light-years away, Proxima Centauri continues burning, indifferent to our struggles, unconcerned with our limitations, simply existing, as it has for billions of years and will for trillions more. When Enrico Fermi asked his famous question in 1950 during a lunch conversation at Los Alamos, he wasn't making a formal scientific argument. He was expressing frustration. The numbers suggested the galaxy should be teeming with civilizations, billions of stars, billions of years for life to evolve. The mathematics of probability made it seem inevitable that we'd have neighbors, lots of them. So where is everybody? 75 years later, we still don't have an answer. The Fermi paradox remains one of the most profound mysteries in science. The silence is deafening. We've searched for radio signals since the 1960s. We've scanned thousands of stars for signs of artificial transmission. We've looked for megastructures, laser communications, atmospheric pollution from industrial civilizations. We've found nothing. Absolute silence across the electromagnetic spectrum. Several explanations present themselves, each more unsettling than the last. The first possibility is that life itself is extraordinarily rare. Maybe the sequence of chemical reactions that leads from molecules to cells happens so infrequently that Earth represents a statistical anomaly. One planet in a trillion that got lucky. Every other world in the galaxy hosts only rocks and gases, and nothing more complex than amino acids. This explanation feels wrong to many scientists. The building blocks of life appear everywhere we look. Amino acids on asteroids, organic molecules in comets, complex carbon chemistry in interstellar clouds. The ingredients are abundant. Mixing them into something living might be rare, but surely not unique across hundreds of billions of stars. The second possibility is that simple life is common, but complex life is rare. Maybe bacteria-equivalent organisms exist on millions of worlds, but the jump from single cells to multicellular life represents a bottleneck so severe that Earth is one of the few places it happened. Multicellular life took billions of years to evolve on our planet. Perhaps that's normal. Perhaps most living worlds remain stuck at the microbial stage indefinitely. If that's true, the galaxy could be covered in slime but devoid of anything that thinks. Proxima b might host bacteria-like organisms that have persisted for billions of years without ever evolving into anything more complex. Life, but not life we'd recognize as interesting. The third possibility is that intelligence itself is rare. Maybe complex life evolves frequently, but the specific environmental pressures and evolutionary accidents that lead to tool-using, technology-developing intelligence happen so seldom that we're alone in the Milky Way. Other galaxies might have intelligent species, but our galaxy drew the short straw. Only one technological civilization among 400 billion stars. This feels unlikely given how intelligence evolved multiple times on Earth through different lineages. Primates developed it. Dolphins and whales show signs of it. Octopuses, with nervous systems completely unlike ours, demonstrate problem-solving abilities that suggest intelligence can arise through radically different evolutionary paths. If Earth alone has multiple examples, surely a galaxy should have more. Which brings us to darker explanations. Maybe intelligent civilizations arise frequently but don't last long. Maybe the gap between developing technology and destroying yourself is measured in centuries. Nuclear war, climate collapse, artificial intelligence gone wrong, bioengineered pandemics, resource depletion. Pick your apocalypse. Perhaps every species that reaches the technological threshold eventually fails to navigate it successfully. This is called the Great Filter Hypothesis. Somewhere between simple organic molecules and galaxy-spanning civilizations lies a barrier that almost nobody crosses. Either the barrier is behind us, in which case we're phenomenally lucky to have passed it, or the barrier is ahead of us, in which case our future is grim. If the filter is ahead, if the silence of the galaxy is caused by civilizations destroying themselves before they can spread to the stars, then every year we survive becomes statistically improbable. Every decade increases the likelihood that our turn is coming. The fact that we've made it this far might just mean we're overdue. An even darker possibility is that advanced civilizations exist but deliberately hide. Maybe there's a reason for the silence. Maybe broadcasting your presence attracts something dangerous. Maybe the galaxy operates under rules we don't understand yet, rules that make visibility lethal. Dark forest theory suggests the universe is like a forest at night. Everyone is hiding, afraid to light a fire or make noise, because predators are listening. If that's true, our radio signals have been announcing our location for a century. Every television broadcast, every radar pulse, every transmission leaking into space has been screaming, "We're here," to whatever might be listening. And if something out there follows dark forest logic, if civilizations that reveal themselves get eliminated, then we've already made a fatal mistake. Or maybe the explanation is simpler and sadder. Maybe interstellar travel is just impossible. Maybe the distances are too vast, the energy requirements too extreme, the physics too unforgiving. Maybe every civilization reaches the same conclusions we're reaching. That leaving your home system requires engineering beyond what chemistry and physics allow. That the galaxy is divided into isolated islands, each occupied by a species that can see their neighbors but never meet them. In this scenario, civilizations might exist on thousands of worlds within a few hundred light years of Earth, all of them trapped, all of them staring at the stars and wondering why nobody visits, all of them developing mathematics and science, and eventually reaching the same depressing answer. That space is too big and light is too slow and physics is too strict. The Alpha Centauri system might host its own intelligent species right now, on Proxima b perhaps, or on a moon of Alpha Centauri A, or on a planet we haven't detected yet. They might have telescopes pointed at Earth. They might have detected our atmospheric oxygen and realized a living world sits just 4 light years away, an impossibly close neighbor by galactic standards, near enough to see clearly, too far to ever reach. And they're sitting there thinking the same thoughts we're thinking. Why haven't the neighbors visited? Are we alone? Is everyone trapped like this? The universe might be full of civilizations having identical crises of isolation. Millions of species scattered across the galaxy, each one imprisoned by physics on their home world, able to communicate only through light-speed signals that take years or centuries to cross the gaps between them. Imagine receiving a radio message from Proxima Centauri tomorrow. Clear, structured, obviously artificial, a greeting in binary, perhaps, or a sequence of prime numbers, proof that someone else is there, proof that we're not alone. How would we respond? We'd send a message back. It would take 4.24 years to reach them. Their reply would take another 4.24 years to return. Every conversation would span almost a decade. You'd ask a question as a young person and receive the answer in middle age. You'd share a joke and get the response after your children had children. And what would you talk about? How do you build a relationship, a culture, a shared understanding with someone you can never meet, someone whose biology might be so different from yours that basic concepts like time or death or emotion don't translate, someone whose civilization might rise and fall in the centuries it takes your transmissions to reach them. We could share science. Mathematics is universal. Physics operates the same everywhere. We could exchange knowledge about our worlds, our suns, our understanding of the cosmos. We could collaborate on problems, sending proposals and receiving critiques decades later. A conversation spread across generations, conducted at the glacial pace of light-speed communication. But we couldn't share lives. We couldn't be friends in any meaningful sense. We'd be pen pals separated by a gulf that makes every letter a historical document by the time it arrives. Our relationship would be asynchronous, built on patience and acceptance that every interaction is a message in a bottle cast into an ocean of time. Some scientists argue that this might be the norm for galactic civilization, not Star Trek, where ships zip between worlds and species meet in person, but a network of isolated cultures connected by slow, patient communication, a galactic internet with ping times measured in years instead of milliseconds, ideas spreading across the stars at light speed, even though physical bodies never do. In this vision, the galaxy could be socially connected despite physical isolation. Knowledge could propagate. Discoveries could be shared. Art and philosophy and science could flow between worlds. The limitation would be time. Every exchange would require patience that spans generations. But it would be something. A civilization that spans light years rather than kilometers. A culture built on delayed gratification and long-term thinking. Perhaps even a better model than our current society, which prizes instant response and immediate satisfaction. Or perhaps it's just a comforting fantasy, a way to tell ourselves that the silence doesn't mean we're alone, that somewhere out there, someone is listening, someone is trying to reach us, handicapped by the same physics that handicaps us. The truth might be lonelier. We might be the first, the earliest intelligence to evolve in this corner of the galaxy. In a universe 13.8 billion years old, someone had to be first. Maybe it's us. Maybe we're the ancient precursors that later civilizations will discover evidence of. Maybe in a million years, when other species reach their technological adolescence, they'll detect our faint radio signals finally arriving after crossing the galaxy, and they'll marvel at how primitive we were, or we might be the last. Maybe intelligence bloomed throughout the galaxy billions of years ago, and we're witnessing the twilight era after everyone else has gone extinct. Maybe the galaxy was once full of voices, and now only echoes remain, ruins on dead worlds, monuments to species that reached for the stars and failed. Either way, the evidence suggests we're functionally alone. Whether because we're rare or early or late or trapped, the result is the same. We occupy a tiny bubble of light and warmth in an ocean of cold darkness. And the walls of that bubble might be permanent. This realization carries philosophical weight that's hard to overstate. Humans have always assumed we're part of something larger. We build communities, nations, civilizations. We find identity in connection to others. The idea that our species might be eternally isolated, that we might never join a galactic community because no such community exists or is accessible, challenges our sense of purpose. If we can never leave, if the solar system is our permanent home, what does that mean for our future? Do we focus inward, building paradise within our limits? Do we terraform Mars and Venus, fill the asteroid belt with habitats, create a thriving civilization confined to one star? Or do we keep reaching outward, sending probes and signals into the void, hoping that someday, somehow, the barriers will fall? Both approaches have merit. Both reflect different aspects of human nature. The urge to perfect our home versus the urge to explore beyond it. The settler versus the wanderer. The gardener versus the pioneer. Maybe we do both. Maybe humanity splits into two philosophical camps. Those who accept the limits and work within them, creating sustainable, rich cultures in the solar system, and those who keep pushing at the boundaries, developing ever more ambitious plans to reach the stars despite the obstacles. The first group builds O'Neill cylinders, rotating habitats that could house millions in comfort between the planets. They mine asteroids, harness solar energy, establish self-sufficient ecosystems that need nothing from Earth. They create art and music and literature that reflects a species at peace with its cosmic neighborhood. The second group launches generation ships, knowing the original crew will die en route. They develop cryogenic suspension, betting that future technology will revive them when they arrive. They send AI-controlled probes, accepting that biological humans might never walk on Proxima b, but perhaps our digital descendants will. They refuse to accept that distance means defeat. Both approaches honor what makes us human, the capacity to build beauty where we are, and the refusal to stop reaching for what seems impossible. Proxima Centauri sits in our sky like a test, a challenge from the universe. Here is the nearest star. Here is a planet that might harbor life. Here is everything you dream about. Now cross 40 trillion kilometers to reach it. Use physics that forbids what you need. Overcome time itself. Find a way or accept that you can't. We haven't answered that challenge yet. We've barely begun trying. But the question hangs over every astronomical discovery, every advance in propulsion, every debate about the future of spaceflight. Are we trapped? Can we escape? Should we try? And perhaps most importantly, if we can't reach Proxima, if the nearest star remains forever beyond our grasp, can we find meaning in a future confined to our solar system? Can we thrive in isolation? Can we build a civilization worth building, even if it never spreads beyond the sun's influence? These questions define our relationship with the cosmos. They separate optimism from pessimism, ambition from acceptance, hope from despair. They force us to confront the possibility that the universe, for all its wonder, might not be designed for exploration. That the very things that make it beautiful, the vast distances, the speed of light, the arrow of time, also make it unknowable. And yet we keep looking. Every night, somewhere on Earth, someone points a telescope at the stars and wonders what's out there, what's possible, what's waiting to be discovered. Because wondering is what we do. Reaching for the unreachable is written into our DNA. Even if we never succeed, even if physics defeats us, we can't stop trying. That persistence might be humanity's greatest quality, or its most tragic flaw. Time will tell, probably a lot of time. Right now, as you're listening to this, Voyager 2 is approximately 20.5 billion kilometers from Earth. That's 137 times farther from the Sun than we are, traveling at 15 kilometers per second relative to our star, moving through a region of space so empty that calling it a vacuum seems like an understatement. The spacecraft is in interstellar space now, beyond the heliopause where the solar wind finally gives up and interstellar medium takes over. Its power output has declined to about 235 watts. That's less than 3 standard light bulbs. Engineers on Earth have been shutting down instruments one by one to conserve energy. The planetary cameras went dark years ago. The ultraviolet spectrometer powered off. The infrared interferometer fell silent. Each shutdown is carefully planned, maximized to extend the mission as long as possible while maintaining the most critical systems. The spacecraft still communicates with Earth. Its radio signal, traveling at light speed, takes more than 19 hours to reach us. When scientists send a command, they wait 38 hours for confirmation that it was received and executed. Nearly 2 full days for a round-trip conversation with a machine we built and launched during the Cold War. By around 2025 to 2030, Voyager 2 will run out of power entirely. The plutonium-238 in its radioisotope thermoelectric generators will have decayed too much to generate sufficient electricity. The transmitter will fall silent. The spacecraft will become a derelict, continuing on its trajectory through the galaxy with no ability to report what it encounters. But it won't stop moving. Momentum doesn't decay in the vacuum of space. Voyager 2 will keep coasting at its current velocity for millions of years. In about 40,000 years, it will pass within 1.7 light-years of the star Ross 248, not close enough to enter orbit or be affected gravitationally, but close by astronomical standards. If any civilization lives in that system, they might detect this ancient probe drifting past, a messenger from a species they'll never meet. Attached to Voyager's side is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images from Earth. Selected by a committee led by Carl Sagan, the record includes greetings in 55 languages, music from cultures around the world, sounds of nature like whale songs and thunder, and 116 images showing what Earth and humanity look like. The record comes with a stylus and instructions, etched in symbolic language showing how to play it and decode the information. The cover is electroplated with a thin layer of ultra-pure uranium-238, which can be used to date the spacecraft by measuring isotope decay. Any civilization that finds Voyager will be able to calculate how long ago it was launched. The music selection is eclectic: Bach's Brandenburg Concerto, Chuck Berry's Johnny B. Good, gamelan music from Java, Navajo chants, Peruvian panpipes. The selection committee tried to represent humanity's diversity while choosing pieces that might communicate emotion and complexity to beings with completely alien cultural contexts. Among the images are photographs of mathematical definitions, the structure of DNA, human anatomy, pictures of Earth from space, and scenes of daily life. A woman in a supermarket, children playing, city streets, agricultural fields, attempts to show who we are and how we live without assuming the viewer shares any of our reference points. The record will last longer than human civilization. Gold doesn't corrode in space. The information etched on its surface will remain readable for billions of years. Long after Earth's continents have shifted, after our sun has entered its red giant phase and consumed the inner planets, Voyager will still be carrying that record through the galaxy, a time capsule from a species that may not exist by the time anyone finds it. There's something deeply moving about that. We launched Voyager knowing it would outlive us. The people who built it, who calculated its trajectory, who selected the music and images, they're all aging or already gone. But their creation continues, a tiny representation of human achievement and human hope drifting through space at 15 kilometers per second, aimed at nothing in particular, carrying a message that might never be received. It's a message in a bottle thrown into the largest ocean imaginable. The odds of anyone finding it are infinitesimally small. The galaxy is vast beyond comprehension. Stars are separated by light years of emptiness. The chance of Voyager passing close enough to an inhabited world for someone to detect and retrieve it approaches zero. But we sent it anyway, because the act of sending matters. The gesture of reaching out, even knowing the reach will probably fail, says something about who we are as a species. We're the creatures who looked at impossible distance and said, let's try anyway. We built a machine to survive for millions of years. We put music and mathematics and photographs on a golden disc and sent it toward the stars. That impulse, that refusal to accept isolation, might be our most defining characteristic. We've been doing it throughout history. Humans have always pushed boundaries, crossed oceans, climbed mountains, ventured into places we weren't designed to survive. Antarctica, the deep sea, the stratosphere, the moon. Each time we conquered one frontier, we look toward the next. Space represents the ultimate frontier, an environment so hostile that unprotected humans die in seconds, distances so vast that even light takes years to cross them, physics so unforgiving that reaching other stars might be permanently beyond our capabilities. And yet we keep trying. We keep designing missions, launching probes, building telescopes, searching for ways to bridge the unbridgeable gaps. Some call this ambition, others call it hubris. Maybe it's both. Maybe the same impulse that drives us to explore also blinds us to our limitations. We're a species that evolved on one planet, adapted to specific gravity and atmospheric pressure and temperature ranges. We're not built for space. Every minute spent beyond Earth's protection requires technology to replace the environment we lost: air, water, pressure, radiation shielding, food, waste recycling. The basics of survival become engineering problems in space. And yet space calls to us. The night sky has fascinated humans for as long as humans have existed. Before we understood what stars were, we told stories about them. We navigated by them. We built monuments aligned with them. We wondered if anyone lived among them. The urge to explore space isn't new. We've been reaching toward the stars culturally and spiritually for millennia. Technology finally gave us the means to reach physically, but the desire was always there. Maybe that desire is universal. Maybe every intelligent species looks up at their night sky and dreams of traveling to those distant lights. Maybe the galaxy is full of civilizations going through exactly what we're going through, discovering the same crushing realities about distance and energy and time, all of them launching their own versions of Voyager, all of them encoding messages they know will probably never be received, all of them hoping anyway. Or maybe we're unique. Maybe something in human psychology makes us different from other intelligent species. Maybe most reach technological maturity and decide the stars aren't worth pursuing. Maybe they focus inward, creating rich cultures within their solar systems, accepting the boundaries physics imposes. Maybe we're the weird ones, the obsessed ones, unable to let go of the dream even when mathematics proves it's futile. There's no way to know. We have a sample size of one technological civilization, one planet that developed complex life, one species that built spacecraft and nuclear weapons and global communication networks. Everything we know about intelligence, technology, and civilization comes from studying ourselves. We have no basis for comparison. That makes every question about our cosmic future speculative. Will we spread beyond Earth? Unknown. Will we reach other stars? Unknown. Will we make contact with other civilizations? Unknown. Will we survive long enough to try? Unknown. We're navigating without a map, making decisions based on incomplete information and untested assumptions. But we're navigating anyway. NASA and other space agencies continue developing plans for missions to the outer solar system. Private companies are building increasingly capable rockets. The Artemis program aims to establish a permanent human presence on the moon. Mars missions are being designed. Concepts for interstellar probes are refined with each passing year. Progress is slow, funding is uncertain, political priorities shift, but the momentum continues. Each generation advances slightly beyond what the previous generation achieved. The Wright brothers flew 120 feet in 1903. 66 years later, humans landed on the moon. The pace of exploration isn't constant, but the direction is consistent. Outward, farther, faster, more ambitious. Whether this trajectory can continue indefinitely is unclear. Maybe we're approaching the limits of what's possible with conventional physics. Maybe the next 100 years will show that certain barriers can't be crossed with any technology we can conceive. Maybe interstellar travel will remain permanently in the realm of theoretical physics rather than practical engineering. Or maybe we'll surprise ourselves. Humans have a history of solving problems that seemed impossible. Heavier-than-air flight was thought to violate physics until the Wright brothers proved otherwise. Splitting the atom was considered fantasy until scientists did it. Landing on the moon seemed like science fiction until it became historical fact. The impossible has a way of becoming merely difficult, then routine, then unremarkable. Perhaps reaching Proxima Centauri will follow the same pattern. Maybe in 2125, 100 years from now, interstellar probes will seem as routine as weather satellites do today. Maybe our descendants will look back at our current limitations the way we look back at sailing ships crossing oceans, amused that people once thought such journeys were at the edge of possibility. Or maybe they'll look back with sadness, realizing we were right, that the stars really are unreachable, that physics really does forbid the travel we dreamed about, that humanity's future really is confined to one solar system, wealthy but imprisoned, able to see infinity but never touch it. The uncertainty is maddening and exhilarating simultaneously. We're living at a unique moment in history, the moment when we first gained the ability to seriously consider leaving our solar system, the moment when we first detected planets around other stars, the moment when we're capable of asking the big questions about our cosmic future but don't yet know the answers. Future generations will know more than we do. They'll have better telescopes, more sophisticated spacecraft, deeper understanding of physics. They'll either confirm our fears about the impossibility of interstellar travel, or they'll prove us wrong in ways we can't currently imagine. But they'll know we're stuck in the uncertainty. Perhaps that uncertainty is the price of living in interesting times. Every era has its great questions. Medieval scholars wondered about the nature of the heavens. Enlightenment thinkers debated human nature. Victorian scientists grappled with evolution and thermodynamics. Our generation's question is whether the universe beyond our solar system is accessible or forever beyond reach. It's a good question to have, a worthy mystery to grapple with. Even if we never solve it, even if we remain trapped by physics and distance, we're living in the moment when humanity first seriously confronted its cosmic limitations. That moment matters. How we respond to it will define us as much as any discovery or achievement. Voyager 2 embodies that moment perfectly. A spacecraft built to explore the outer planets that ended up leaving the solar system entirely. A machine that exceeded its design parameters by decades. A messenger carrying our music and greetings towards stars it will take tens of thousands of years to reach. Voyager represents ambition and limitation intertwined, success that's also failure, achievement that's also defeat. The spacecraft fulfilled its mission beautifully. It visited Jupiter, Saturn, Uranus, and Neptune. It sent back data that revolutionized our understanding of the outer solar system. It discovered moons and rings and magnetic fields. It functioned far longer than anyone expected. By every reasonable metric, Voyager 2 is one of the most successful space missions ever launched, and yet it will never reach another star. Despite traveling at 55,000 kilometers per hour, despite decades of flight, despite crossing into interstellar space, Voyager won't arrive at another solar system for 40,000 years. The nearest star remains impossibly far even for our fastest messenger. That juxtaposition captures our current relationship with space. We can do amazing things. We can send machines to the edge of the solar system. We can detect planets around distant stars. We can calculate the chemistry of alien atmospheres from light years away. We can map the structure of the entire observable universe. Our capabilities are genuinely extraordinary, but some things remain beyond us. The gaps between stars are too wide. The energy requirements are too extreme. The timescales are too long. We're powerful but not powerful enough. Advanced but not advanced enough. Ambitious but limited by physics that won't bend no matter how desperately we push. Living with that contradiction requires a certain kind of acceptance. We have to embrace both what we can do and what we can't, celebrate our achievements while acknowledging our limitations, dream of the impossible while working within the possible. It's a delicate balance. Too much focus on limitations breeds despair. Too much focus on dreams breeds delusion. Perhaps the healthiest approach is to accept uncertainty as permanent. We don't know if interstellar travel will ever become practical. We might learn something that changes everything, or we might not. Either way, the work continues. We keep exploring, keep building, keep reaching, not because we're guaranteed to succeed, but because reaching matters regardless of success. Voyager 2 proves that reaching matters. The golden record will likely never be found, but creating it had value. The act of thinking about what to include, how to encode it, what message to send, that process revealed something about humanity. We're the species that sends music to the stars. That impulse says something beautiful about us even if nobody ever hears the music. Maybe that's enough. Maybe the journey is the destination in a very literal sense. Maybe trying to reach Proxima Centauri matters more than actually arriving. Maybe launching Voyager matters more than whether anyone finds it. Maybe asking the questions about our cosmic future matters more than having answers. Or maybe that's just rationalization. Maybe we're telling ourselves the journey matters because we know we'll never complete it. Maybe future generations will look back and see our space exploration as a brief phase before we accepted our limits and stopped trying. Maybe Voyager will be remembered as the high water mark, the farthest we ever reached before we gave up. Time will tell. Probably a lot of time. Centuries, maybe millennia. The scales on which these questions play out exceed human lifetimes by orders of magnitude. We won't see the resolution. We're just one moment in a much longer story. Our job is to do what we can with what we have and pass the work to whoever comes next. Voyager is doing that, still functioning, still transmitting, still carrying our message even as its power fades. In a few years it will fall silent, but until then, it keeps working, keeps doing its job, keeps representing humanity in the most remote environment any human creation has ever reached. That persistence, that refusal to quit even when the goal is impossible, might be our most important legacy. Not what we achieved, but that we tried, that we built something to last millions of years and sent it toward infinity, knowing it would never arrive. That kind of hope, that kind of defiance, that kind of stubbornness in the face of cosmic indifference, that's worth something. Maybe that's worth everything. There's a photograph that changed how we see ourselves. Taken by Voyager 1 in 1990, from a distance of 6 billion kilometers, it shows Earth as a pale blue dot suspended in a sunbeam. Carl Sagan, who suggested the photograph be taken, later wrote about what it meant. That tiny pixel, barely visible against the cosmic dark, contains everything we've ever known, every human who ever lived, every civilization, every war, discovery, triumph, and tragedy, all of it happening on a mote of dust suspended in a sunbeam. That perspective matters when we talk about reaching other worlds, because from any reasonable cosmic distance, Earth disappears entirely. Our planet, which feels so large when you're standing on it, becomes invisible when viewed from even modest astronomical distances. From Proxima Centauri, Earth would be completely undetectable without a telescope. Our sun would be just another star in a crowded sky. Finding Earth among all those other lights would require knowing exactly where to look and having instruments sensitive enough to detect the minute wobble or slight dimming that betrays a planet's presence. We've managed to detect thousands of exoplanets using those techniques, watching stars wobble, measuring brightness dips when planets transit, analyzing light spectra for chemical signatures. Our telescopes can characterize atmospheres of planets hundreds of light years away. We know the composition of alien air on worlds we'll never visit. The James Webb Space Telescope can detect water vapor, methane, carbon dioxide, even potential biosignatures in the atmospheres of distant planets. But detecting something and reaching it remain entirely different challenges. We can see Proxima b. We can measure its size, estimate its temperature, speculate about its atmosphere. We can point our most powerful instruments toward it and gather data. But crossing the 4 light years to actually arrive there requires solving problems we haven't solved, may never solve. The SETI Institute has been searching for radio signals from extraterrestrial civilizations since 1984. The Allen Telescope Array in Northern California scans the sky continuously, listening for patterns that might indicate artificial origin. 42 antennas, each 6 meters in diameter, working together to detect signals across billions of radio channels simultaneously. The array can observe multiple star systems at once, multitasking between conventional astronomy and the search for alien transmissions. In all those years, across all those observations, encompassing thousands of star systems, they've found nothing. Absolute silence, no narrowband signals, no obvious artificial patterns, no hello broadcast from civilizations eager to make contact. The galaxy, at least the portion we've examined, appears devoid of technological societies broadcasting their presence. This silence haunts researchers. Either we're alone, which seems statistically unlikely given the billions of stars and planets, or we're missing something fundamental. Maybe civilizations don't broadcast once they reach a certain technological level. Maybe they use communication methods we haven't discovered yet. Maybe they exist, but remain deliberately quiet for reasons we don't understand. Or maybe they're all trapped like us. Maybe every civilization reaches the same walls we're hitting: the speed of light, the rocket equation, the impossibility of crossing interstellar distances with conventional physics. Maybe the galaxy is full of species staring at their skies, detecting each other's planets, and realizing they'll never meet. That possibility feels almost worse than being alone. To know others exist, to confirm we're not unique, but remain forever separated by physics that won't bend. Prison bars made of space-time and energy requirements. Neighbors close enough to see but too far to visit. Yet humans keep searching, keep building instruments, keep pointing antennas at the stars and listening, The SETI effort continues despite decades of silence because the implications of detection would transform everything. One confirmed signal from an alien civilization would answer the oldest question we've asked. We'd know finally and definitively that we're not alone, even if we could never reach them, even if communication took decades per exchange, even if the physical meeting remained impossible. Just knowing would matter, understanding that other minds evolved somewhere else, that intelligence arose independently, that we're part of a larger community of conscious beings scattered across the cosmos. That knowledge would reshape philosophy, religion, science, culture. Everything would change. But until detection happens, we're left with uncertainty, with the pale blue dot perspective showing how small and isolated we are, with the mathematics proving how far away everything else is, with the physics demonstrating how hard crossing those distances would be. Some people find this depressing. The cosmic perspective can make human concerns seem trivial. If we're just specks on a dust mote in a vast, uncaring universe, why does anything matter? If we can never leave our solar system, if we're permanently confined to this tiny corner of space, why bother trying? But there's another way to look at it. The cosmic perspective can also make human achievements seem miraculous. We're matter that became self-aware, atoms arranged in patterns complex enough to contemplate their own existence. We're the universe experiencing itself, thinking about itself, trying to understand itself. That's extraordinary, regardless of whether we can travel to other stars. We've accomplished things our ancestors would have called impossible: flight, space travel, splitting atoms, mapping genomes, connecting billions of people through global communication networks, detecting planets around distant stars, landing robots on Mars, sending spacecraft beyond the solar system. Each generation pushes boundaries their predecessors couldn't imagine crossing. Maybe interstellar travel follows the same pattern. Maybe what seems impossible now becomes routine later. History suggests that betting against human ingenuity is usually a mistake. We've solved problems that initially appeared insurmountable. We've developed technologies that once existed only in fiction. We've repeatedly demonstrated that limits are often temporary, confined to current knowledge and current capabilities. Or maybe this time really is different. Maybe some limits are permanent. Maybe physics really does forbid what we want to do. Maybe we've hit a wall that engineering can't overcome, no matter how advanced we become. Living with that uncertainty requires a particular kind of courage. We have to work toward goals we might never achieve, build things that might fail, dream dreams that might prove impossible, and do it anyway because trying matters regardless of outcome. Children growing up today will likely see things we can't imagine. Colonies on Mars, perhaps, mining operations in the asteroid belt, permanent human presence beyond Earth. They might see probes launched toward Proxima Centauri, using technologies we're only beginning to develop: laser-pushed solar sails, compact fusion reactors, propulsion systems that make current rockets look primitive. Those children might live to see data return from another star system, images of Proxima b from close range, measurements confirming or denying the presence of life, answers to questions we've been asking for generations. They might witness humanity's first confirmed contact with something beyond Earth, whether that's microbial life on Europa or intelligent signals from across the galaxy. Or they might witness our species accepting limitations, deciding that the solar system is enough, that we don't need to reach other stars to have meaningful existence. That building paradise within our boundaries matters more than expanding beyond them, that the journey inward toward understanding consciousness and creating flourishing civilizations matters more than the journey outward toward other worlds. Both futures are possible, both have merit, both reflect valid approaches to the questions we face. What we've learned on this journey from Uranus to Proxima Centauri is that distance in space represents more than geometry. It's a fundamental barrier built into the structure of reality. Light speed isn't just fast, it's the ultimate speed limit enforced by the universe itself. Time isn't uniform, it stretches and compresses depending on velocity. Space isn't static, it expands, carrying galaxies away from each other faster than any rocket could chase. We've learned that Uranus, the frozen giant on the edge of our solar system, took 9 years to reach with our fastest spacecraft. That Proxima Centauri, the nearest star, would take 80,000 years to reach at the same speed. That the gap between those numbers isn't a challenge to overcome, but a mathematical truth about how space and motion relate. We've learned that the universe makes some things easy and other things impossible. Easy to see distant galaxies, impossible to visit them, easy to detect exoplanets, impossible to walk on them, easy to calculate what it would take to travel between stars, impossible to generate that much energy or survive that much time. We've learned that isolation might be permanent, that the cosmic perspective perspective reveals us as extraordinarily alone, whether we're the only intelligence in the galaxy or simply one of many who can never overcome the barriers between us. But we've also learned that humans don't accept isolation gracefully. We keep reaching, keep building, keep dreaming, not because we're guaranteed to succeed, but because reaching matters regardless of success. Because the act of trying says something about who we are. Because curiosity and ambition and hope are fundamental to human nature. Voyager 2 carries our message toward the stars, knowing it will probably never be received. The golden record spins silently through the interstellar medium, preserving music and greetings and images for civilizations that may not exist. That act of hope, that gesture toward an unknowable future, matters more than whether anyone ever finds it. We point radio telescopes at distant stars, knowing we probably won't hear anything. But we listen anyway because the implications of detection would be profound, because the question of whether we're alone demands we search for answers even if the search takes generations. We study Proxima b knowing we can't reach it, but we study anyway because understanding matters, because knowledge has value independent of application, because wondering what that distant world looks like, whether it has oceans and continents, whether life evolved there, those questions drive us forward even when the answers don't change our practical situation. The journey from Uranus to Proxima Centauri isn't really about distance. It's about confronting our limits and deciding how to respond. Do we rage against them, accept them, work within them, transform them? All of the above? Different people will answer differently. Some will dedicate their lives to developing technologies that might enable interstellar travel. Others will focus on making the solar system hospitable. Some will search for alien signals. Others will build art and culture and civilization right here on Earth. All of these approaches honor our nature as explorers, thinkers, and dreamers. What matters is that we continue, that we don't give up because the challenges are large, that we don't despair because the universe is vast, that we find meaning in effort rather than only in achievement, that we measure progress in generations rather than years. The story of how humanity responds to cosmic isolation hasn't been written yet. We're living in the opening chapters, the moment when we first understood the scale of the universe and the barriers to exploring it. The moment when we detected thousands of exoplanets and realized how many worlds exist beyond our reach. The moment when we sent our first messengers beyond the solar system knowing they'd never return. Future chapters will be written by people not yet born. They'll have better tools, deeper understanding, longer perspectives. They'll look back at our time and see us as either the generation that gave up or the generation that persisted, either the moment when humanity accepted its limits or the moment when we decided limits were just problems waiting to be solved. We can't know which future awaits. We can only decide what we do now, how we allocate resources, what questions we prioritize, what missions we launch, what dreams we nurture. Those decisions accumulate into a direction, and that direction determines where we end up. Proxima Centauri will still be there regardless of what we decide, 4 light-years away, burning its faint red light, orbited by at least one planet that might host life, waiting, patient, indifferent to our struggles. Just another star in a galaxy of 400 billion stars, each one potentially surrounded by worlds we'll never see. But among all those stars, Proxima is special to us, because it's the nearest, because we can actually contemplate reaching it someday, because it represents the boundary between what we can do and what we dream of doing, because it forces us to confront questions about who we are and what we want to become. And that confrontation, that wrestling with cosmic questions that have no easy answers, might be exactly what we need. Maybe struggling with impossible challenges makes us better. Maybe dreaming of unreachable destinations gives life meaning. Maybe the journey matters more than the destination because the journey changes us in ways that arriving never could. We'll keep looking at the stars, keep wondering what's out there, keep building instruments to see farther and understand deeper, keep launching probes toward the edge of our capability, keep searching for signals and signs of life, keep dreaming about the day when the barriers fall and we finally reach beyond our cosmic neighborhood. And if that day never comes, if physics proves stronger than our engineering, if distance remains unconquerable, we'll still have tried. We'll still have reached as far as possible. We'll still have asked the questions and sought the answers and refused to accept ignorance as permanent. That persistence, that refusal to quit might be our greatest achievement, greater than any distance traveled or any world reached, because it means we're the species that looked at infinity and said, let's go there anyway, even knowing we might never arrive. Tonight, somewhere on Earth, a child is looking up at the stars for the first time. Maybe they're in a backyard in Texas, lying on grass still warm from the afternoon sun. Maybe they're on a rooftop in Mumbai, surrounded by the glow of city lights that wash out most of the sky but can't hide the brightest stars. Maybe they're in rural Scotland, wrapped in blankets against the cold, watching the Milky Way arc overhead like a river of light. And they're asking the same question humans have asked for thousands of years. What's out there? Can we go there? Are we alone? We still don't have complete answers. After centuries of astronomy, decades of space exploration, years of detecting exoplanets and studying distant stars, we still face fundamental uncertainty about our place in the cosmos. We know more than any previous generation. We've sent machines to every planet in our solar system. We've detected thousands of worlds orbiting other stars. We've measured the composition of alien atmospheres from dozens of light years away, but knowing what's out there and reaching what's out there remains separated by a gap that might never close. We can see paradise, we can study it, we can calculate its distance, measure its properties, even estimate its habitability, but touching it, walking on its surface, breathing its air if it has any, might remain forever impossible. That gap has been the subject of this entire journey. From Uranus, the frozen giant that took 9 years to reach with our fastest spacecraft, to Proxima Centauri, the nearest star that would take 80,000 years to reach at the same speed. From diamond storms falling through methane atmospheres to potentially habitable worlds orbiting red dwarf stars. From the physics that limits our speed to the biology that limits our lifespan, we've explored the barriers, the rocket equation that makes fuel requirements spiral into impossibility, the speed of light that functions as an ultimate cosmic speed limit, time dilation that transforms space travel into time travel, the interstellar medium that becomes a sand-blasting wind at relativistic speeds, the sheer, incomprehensible vastness of the distances between stars. Each barrier is real. Each one is grounded in fundamental physics rather than engineering limitations. We're not failing to reach other stars because we lack the right technology. We're failing because the universe has built walls into the structure of space-time itself, walls that don't bend regardless of how hard we push. And yet, here we are, still pushing, still designing missions, still launching probes, still searching for signals, still refusing to accept that impossible means permanent. That refusal defines us as a species. We're the creatures who looked at the sky and decided we belonged there, who saw mountains and climbed them, who encountered oceans and crossed them, who faced deserts, ice caps, jungles, and every hostile environment Earth offers, and survived in all of them. We're adaptable, curious, stubborn to the point of absurdity. Space is just the latest hostile environment we're trying to conquer. Harder than any we've faced before, maybe harder than biology allows us to conquer. But we're trying anyway. In 2025, as you're listening to this, space agencies around the world are planning missions that would have seemed like fantasy 50 years ago. Commercial companies are launching satellites by the hundreds. Reusable rockets land themselves after delivering payloads to orbit. Permanent bases on the moon are being designed. Mars missions are progressing from concept to engineering. The James Webb Space Telescope continues analyzing atmospheres of exoplanets, searching for biosignatures that might indicate life. Progress happens slowly, but it happens. Each year we push a little farther. Each decade brings capabilities that the previous decade lacked. The trajectory is clear, even if the destination remains uncertain. Maybe in 50 years we'll have permanent settlements on Mars, habitats in the asteroid belt, mining operations throughout the solar system, a human presence that extends from Earth to the Kuiper belt. Maybe we'll have sent laser-propelled probes toward Proxima Centauri, waiting decades for data to return, but knowing the journey has begun. Or maybe in 50 years we'll have accepted our limits, decided that the solar system provides enough room for human expansion, that we don't need other stars to have meaningful existence. That building paradise within our boundaries matters more than reaching beyond them. Both futures are valid. Both reflect different aspects of human nature. The explorer versus the settler, the wanderer versus the gardener, the dreamer versus the pragmatist. What matters is that we continue asking the questions, that we don't stop wondering what's possible, that each generation pushes a little farther than the one before, even if that push sometimes means accepting limitations and working within them rather than against them. Voyager 2, still coasting through interstellar space with failing power and fading transmitter, embodies this perfectly. A machine that exceeded every expectation, that visited worlds we'd never seen up close, that sent back data revolutionizing our understanding, that continued functioning decades beyond its design lifetime, that carried our message towards stars it will never reach. Success and failure intertwined, achievement that's also limitation, a reminder that trying matters regardless of whether we achieve the ultimate goal. The golden record spins silently on Voyager's side. side. Music from Earth, greetings in 55 languages, images showing who we are and how we live, a message in a bottle thrown into an ocean so vast that recovery seems impossible. But we sent it anyway, because the act of reaching out matters, because hope matters, because connecting, even across impossible distances, even knowing connection might never happen, says something beautiful about who we are. We're the species that sends music to the stars, that encodes mathematics and chemistry and biology onto golden disks and launches them toward infinity, that refuses to accept isolation as permanent even when physics proves isolation is real. That stubbornness, that defiant hope, might be our greatest quality or our greatest flaw. History will judge. But either way, it's ours. It defines us, makes us human in ways that nothing else does. Proxima Centauri will still be there tomorrow, 4.24 light-years away, burning its faint red light, orbited by planets we've detected but will likely never visit, waiting with the patience of astronomical time for something to reach it, if anything ever does. The distance hasn't changed. The physics hasn't changed. What's changed is our understanding. We know what's out there now. We know how far away it is. We know how hard reaching it would be. We know the barriers we face. And we're still trying anyway, because that child looking at the stars tonight deserves a future where trying matters, where curiosity is rewarded, where difficult problems receive serious attention, where humanity continues reaching even knowing the reach might fail. We owe them that. We owe ourselves that. We owe the universe that, to be the species that looks at impossible challenges and says, let's try anyway. Maybe we'll succeed. Maybe physics will reveal loopholes we haven't found yet. Maybe engineering will develop technologies that make the impossible merely difficult. Maybe that child looking at the stars will grow up to work on missions that actually reach Proxima Centauri, sending back data from another star system within their lifetime. Or maybe they'll grow up accepting limitations we're only beginning to understand. Maybe they'll focus on making the solar system hospitable rather than reaching beyond it. Maybe they'll build civilizations within our cosmic neighborhood that thrive despite, or perhaps because of, their isolation. Either way, they'll inherit a species that tried, that launched Voyager, that detected thousands of exoplanets, that studied Uranus and Neptune and every world within reach, that built telescopes powerful enough to analyze alien atmospheres, that sent robots to Mars and probes beyond the solar system, that refused to accept ignorance as permanent or distance as absolute defeat. That legacy matters, that persistence through difficulty, that embrace of uncertainty, that willingness to work on problems spanning generations. Those qualities will serve humanity regardless of whether we ever leave our solar system. Because the real journey isn't from Earth to Proxima Centauri. The real journey is from ignorance to understanding, from isolation to connection, from acceptance of limits to pushing against them. That journey continues regardless of whether our physical bodies ever reach other stars. We're learning, growing, expanding our knowledge even when we can't expand our territory. Each discovery about Uranus teaches us about planetary formation. Each detection of an exoplanet tells us something about how solar systems develop. Each failed rocket launch reveals what doesn't work, guiding us toward what might. Each question we answer raises new questions worth asking. That process, that endless curiosity driving us forward, matters more than any destination. The work itself has value. The trying has meaning. The reaching, even toward unreachable goals, makes us better. So here's what I want you to do. Tonight, or whenever you have the chance, go outside and look up. Find a dark spot if you can, away from city lights. Let your eyes adjust to the darkness and really look at the stars. Each one is a sun. Many have planets. Some of those planets likely host life. A few might have civilizations looking back at us, wondering if they're alone, facing the same barriers we face, asking the same questions we ask. The distances between us might never be crossed. The physics might never allow meeting. But for a moment, looking up at that sky full of stars, you're connected to something larger than yourself. You're part of a species that looks at infinite space and refuses to accept that infinite means unreachable. That matters. You matter. Your curiosity matters. The questions you ask matter. The work being done by scientists and engineers and dreamers around the world matters. We might never reach Proxima Centauri, but we're trying. And in that trying, in that refusal to quit, in that stubborn human insistence on pushing boundaries, we find meaning that transcends success or failure. The universe is vast beyond comprehension, cold beyond imagination, empty beyond any earthly experience of emptiness. It's indifferent to us, uncaring about our survival, unimpressed by our achievements. But we're here anyway, looking up, wondering, reaching, refusing to accept that vastness means we should stop trying, building machines to cross distances we can barely calculate, encoding messages to civilizations that might not exist, dreaming of futures we might never see, and that, more than any distance traveled or any world reached, proves that humans are extraordinary. We're matter that thinks, atoms that wonder, stardust contemplating stars. Proxima Centauri is 4 light-years away. That's both impossibly close and impossibly far. Close enough to see, too far to touch. The perfect metaphor for the human condition. We're surrounded by wonders we can observe but not possess, beauty we can admire but not own, mysteries we can study but may never fully solve. Learning to live with that, to find meaning in observation rather than possession, in wondering rather than knowing, in trying rather than succeeding, that might be the real lesson of interstellar distance. We are, each of us, explorers, not because we travel far, but because we ask questions, not because we conquer space, but because we refuse to let space defeat us, not because we reach the stars, but because we keep trying to reach them even when mathematics says we can't. That's enough. That has to be enough. Because it's all we have, and it's more than most species will ever have. The capacity to wonder, the intelligence to ask questions, the tools to seek answers, the stubbornness to keep trying despite overwhelming odds. Voyager 2 drifts through darkness, carrying our message. Uranus spins on its side, dropping diamond rain through frozen clouds. Proxima Centauri burns red and small, orbited by worlds we'll probably never walk on. And here, on Earth, humans keep looking up, keep building, keep dreaming. That's our story. That's who we are. That's what makes this tiny pale blue dot matter in a universe that doesn't care whether we exist. We care, we wonder, we try, and as long as we keep doing that, as long as that child looks at the stars and asks, "What's out there?" we win, regardless of whether we ever reach Proxima Centauri. The journey continues. Thank you for taking it with me. If this exploration meant something to you, if these questions matter to you, share this. Talk about it. Keep the conversation going. Subscribe if you want more journeys through space and science and the limits of human capability. Comment with your thoughts about whether we'll ever reach other stars, or whether we should even try. Because these questions don't have single answers. They require conversation, debate, exploration. They need each generation to wrestle with them anew, bringing fresh perspectives to ancient problems. The stars are waiting, not with answers, just with more questions. And that's perfect, because questions are what make us human. Keep looking up.